Hello dear students, I'm Praveen, your chemistry educator. Students, in this video, what we are going to do, we are going to cover the full Ionic Equilibrium chapter. Now, I know very well that many students feel that Ionic Equilibrium is one of the toughest chapter we have in the chemistry, right? But believe me, right, one thing is there, like no doubt Ionic Equilibrium is a tough chapter, right? I cannot deny that fact, right? There are concepts in Ionic Equilibrium, right, which you need to learn a lot, right? In those concepts, you have to memorize lots of things, lots of formulas. But the point is, if you don't look into the chapters, like when you open a book, right? So in your book, in the Ionic Equilibrium chapter, you have so many content, right? If you do not follow that, if you focus on that point, that what type of question we get in the NEET examination, right? So if you focus completely on the NEET part, what type of problems we get in the NEET examination, then it will be easier for you. Because what I feel, in the NEET examination itself, we never get very much tough question from this chapter, right? So instead of focusing on what we have in the Ionic Equilibrium chapter, it's better to focus on what we get, right, in the NEET examination from this Ionic Equilibrium chapter, and then you can say this chapter will become easy for you, right? Of course, in this session, I will be discussing about all the topics that we have in the Ionic Equilibrium, right? And later on, your task will be to practice more and more questions from this chapter, because you know that in physical chemistry, right, solving problems is the major point, right, for the completion of the chapter. And for your practice, right, we are providing the DPPs in the video description. So from video description, you can download those DPPs, right, and you can practice. And not only that, those DPPs you can also get on the PW app. So download the PW app, and just like lakhs of students, you can also start your NEET journey with PW. So now students, let's start this session, right, with the very first thing, that is, what are the topics that we will be covering in this session. So we will start with, first thing is, what is the meaning of electrolyte, what are the types of electrolyte. Then we will talk about the major part of the chapter. You know that in Ionic Equilibrium, we mainly deal with what is acid, base, and those pH calculations. So we'll talk about what are the concepts of acid, base we have. Then a very, very useful term, that is degree of dissociation and dissociation constant, along with what is Ostwald dilution law. Then we will move into the pH scale part, where you will see lots of pH calculation, right? We have multiple cases here, right? Calculation of pH of strong acid, strong base, weak base, pH of salts, buffers and all, right? So in pH calculation only, you can say that we have salt hydrolysis, where basically we talk about how to calculate pH of different types of salt. Then we will talk about a very, very interesting and important point, that is a common ion effect. And finally, we will see buffer solution and solubility product. But at the end, we will also see what is the meaning of acid-base titration, and especially when we do acid-base titration, right? So what types of indicator we use in them, right? So let's begin with the very first thing, that is electrolytes. Now, I hope you all know what is electrolyte. Basically, electrolyte is that substance, right, which furnishes or produces, ions in solution, right? This is the fundamental meaning of your electrolyte. Any compound, if it is an electrolyte, so when you dissolve that compound in water, so after going into water, it can produce certain ions, right? And if your compound is not able to produce ion in solution in water, so then your compound will be called as non-electrolyte. Now, students, please try to understand that when it comes to electrolyte, so for electrolyte, we have almost 3 chapters in chemistry, right? Only about electrolyte, right? On the basis of the compound electrolyte, we have created 3 chapters in chemistry. One is this Ionic Equilibrium, one more is there redox reaction, and one more is there electrochemistry. So in these 3 chapters, you talk about only electrolytes or their functions or their properties, right? If I give you certain example, so NaCl, right? When you dissolve NaCl in water, so that can give you Na plus and Cl minus ion. So I can say that NaCl is an electrolyte. Then if I talk about ammonia, so when we dissolve NH3 in water, so it produces ammonium ion, NH4 plus ion along with OH minus ion. So I can say that definitely ammonia is also an electrolyte. So any compound, if it will produce ion in solution in water, then that compound will be called as electrolyte. But suppose if I dissolve methane gas or oxygen gas or nitrogen gas in water. So I hope you know very well that when we dissolve methane, oxygen, nitrogen in water, they will not produce any ion, right? So that means what? These compounds which cannot produce ion, they will be called as non-electrolyte. So my point is, you should be very much clear in this chapter, in this Ionic Equilibrium chapter, regarding what is electrolyte and what is non-electrolyte. Electrolyte means those compounds which will produce ions in solution. When you dissolve in water, they will produce ion. And non-electrolyte means those compounds which will not be able to produce ions in solution. Now, when it comes to electrolyte, if you focus on electrolyte, so electrolyte we classify into two categories, right? We have two types of electrolyte. One is called strong electrolyte, and the other one is called weak electrolyte. And believe me, the name strong and weak electrolyte is completely opposite, right? Opposite from their properties, right? An electrolyte is called as strong electrolyte when it is completely dissociated. When it is completely dissociated. Right? And an electrolyte is called as weak electrolyte when it is partially ionized or partially dissociated. Now, please try to understand, when I say that strong electrolyte is completely ionized or completely dissociated and weak electrolyte is partially ionized or partially dissociated, so what is the exact meaning of it? Its exact meaning is, on the basis of amount, please try to understand, on the basis of amount. Suppose I take 10 moles of an electrolyte, and when I dissolve 10 moles of electrolyte in water, right, if the whole 10 mole is dissociating into ions, if the whole amount, if the total amount of electrolyte is decomposing into ions, so then it is called complete dissociation, then it is called strong electrolyte. But on the other hand, suppose that I took another electrolyte, again I took 10 moles, but out of 10 moles, only certain amount is getting dissociated. Like I dissolved 10 moles of an electrolyte, but after going into water, out of 10 moles, suppose only 4 moles are dissociating, and the rest 6 moles of electrolyte is not dissociating. So that means what? We are having partial dissociation. Out of 10 mole, only 4 mole is dissociating. So then this electrolyte will be known as weak electrolyte. So of course, strong electrolyte means complete dissociation, weak electrolyte means partial dissociation. But at the same time, you need to understand that we say complete and partial dissociation on the basis of amount, right? How much amount is getting dissociated out of total amount. Like for example, if I take again HCl, hydrochloric acid, right? And if you take suppose 5 moles of hydrochloric acid, right? So initially you will have HCl molecules in the pure form. Now, as soon as you dissolve HCl into water, it will ionize into H plus ions and Cl minus ion. Now, suppose if I consider that state when dissociation has not happened, or I can say before dissociation, So before dissociation, I have only the molecule HCl, which is 5 mole. And of course, if dissociation has not happened, so the amount of ions will be 0, right? Initially or before dissociation. Now, point is, if I say that HCl is strong electrolyte, so that means what? Whatever amount I will take, right, the whole amount will dissociate. So finally, after dissociation, in this case, in case of HCl, I can say this 5 mole will become 0 mole. Means all the 5 mole of HCl molecule will break, and finally the molecule will become 0. Now I don't have final any kind of molecule, any number of molecule in the solution. So the molecule will become 0, And according to stoichiometry, I hope that you people are good in stoichiometry calculation, right? So according to stoichiometry, if I see, so 1 mole of HCl can produce 1 mole of H plus and 1 mole of Cl minus. So automatically 5 moles of HCl, if it will dissociate completely, it will produce what? 5 mole of H plus and 5 mole of Cl minus. So this is what I was trying to say. In case of HCl, whatever amount I took, that means 5 mole, the whole amount is dissociating. That means I can say that HCl is strong electrolyte. HCl is strong electrolyte, right? But instead of HCl, and I took one example also, you need to remember in this chapter some of the strong and weak electrolytes, and of course HCl is one of the example of strong electrolyte, right? But on the other side, if you talk about weak electrolyte, right? So if I say in general that AB is one of the example of weak electrolyte, so AB will decompose into A plus ion and B minus ion. Now if AB is weak electrolyte, please focus here. I am saying that initially I took 5 moles of AB. So again initially, because this is the condition when dissociation has not begun, right? So before dissociation, the amount of ion here also it will be 0. Now if I took 5 moles of AB, and if AB is weak electrolyte, then in this case complete dissociation will not happen. The whole 5 mole will not decompose, the whole 5 mole will not break. So out of 5 mole, certain moles will break, certain amount will break. Now here let's assume that out of 5 mole, X moles of AB is dissociating. So that means what? After dissociation, this will not become 0. This will become 5 minus X. And again, using stoichiometry, you can say that 1 mole of AB can produce 1 mole of A plus, 1 mole of B minus. So if X moles of AB is getting dissociated, so I will be getting X moles of A plus and X moles of B minus. So partial dissociation means whatever initial amount of electrolyte you will take, the whole amount will not break. Out of the total amount, only certain amount will break. And when you say complete dissociation for strong electrolyte, so that means what? Whatever amount of electrolyte you will take, the whole amount will break, right? The molecule will become 0 and you will have only ions. One more point you can notice here, right? Because these small points will help you in this chapter. Please try to understand. Whenever you will take a solution of strong electrolyte, so in the solution of a strong electrolyte, you will have only ions. You won't find any molecule. Like if I create a solution of HCl in water, right? So HCl will be present only in ionic form, means H plus and Cl minus, right? In the solution of HCl, you won't have HCl molecules in it. HCl molecules will not be present because HCl is strong electrolyte. So in case of strong electrolyte solution, you have only ions, you have no molecules. But when you talk about weak electrolyte, right? So in the solution of weak electrolyte, students, you will have ions as well as molecules. You will have both. Like here, if AB is weak electrolyte and I prepare a solution of AB, so in the final solution, I will have A plus ions, B minus ions, and along with that, I will have AB molecules also. So in this case, in the solution of weak electrolyte, you will have molecule also and you will have ion also. And that's why we are calling it ionic equilibrium. Because in case of weak electrolyte, students, equilibrium is established between the molecule and the ions. You have an equilibrium state, right, between your molecule and ions, right? So obviously equilibrium will be established only in case of weak electrolyte, not in case of strong electrolyte. But please always remember in your mind that when we have strong solution, strong electrolyte solution, so it contains only the ions of electrolyte, no molecule. And when we have solution of weak electrolyte, so that contains ions as well as molecules in the solution. And there we have equilibrium between the molecules of the electrolyte and ions of the electrolyte. So now I think you have understood one point, that ionic equilibrium chapter starts with the concept of electrolyte. You should have a good knowledge of electrolyte. what is electrolyte, what is non-electrolyte, what is a strong electrolyte, what is weak electrolyte, and what is the meaning of strong and weak electrolytes. Right? Now, point is, after understanding strong and weak electrolyte, I hope at least you all have understood what is strong electrolyte, what is weak electrolyte. After understanding electrolyte, the next point we have is acid base, right? Concept of acid base in this chapter. And from this moment, throughout the chapter, you will be talking about only acid base and their properties. But the reason is why we talk about acid base in this chapter. Because acids and bases are nothing but examples of electrolyte. Students, please try to understand, like you start this topic from your class 10th, right? In your 10th class, you have a chapter known as acid, base and salt, right? Acid, base and salt. Now in this chapter, in this ionic equilibrium chapter, why we are talking about acid, base and salt? Because these acid, base and salts, they are nothing but they are examples of electrolyte. All the acids, all the bases, all the salts, they are electrolyte, either strong or weak, right? And if an acid is a strong electrolyte, then that acid is called as a strong acid. If an acid is weak electrolyte, then that acid is called as weak acid. Same thing for base also. If you have a base which behaves like a strong electrolyte, so that base is called as a strong base. And if you have a base which behaves like an weak electrolyte, so then that base is called as what? Weak base. So you will see examples of a strong, weak acids and base in this example. But first point is, you need to understand that we are talking about acid, base and salt in this chapter because they are the examples of electrolyte. They are the examples of electrolyte. Now, of course, when it comes to acid and base, so if I go into the history, so with time, we got different concepts of acid, base, right? And the very first concept that you need to know is the concept of Arrhenius, right? And let me tell you one thing. In your 10th class, when you talk about acids and base, so in your 10th class, you talk about this, Arrhenius acid and Arrhenius base. Basically, what Arrhenius said, that any compound which can donate H plus ion in solution. So Arrhenius said, according to Arrhenius, if any compound is there, if any electrolyte is there, and in water it can donate H plus ion, so then that compound, that electrolyte, we will term as acid, right? For example, you take HCl, you dissolve HCl in water, it will give you H plus ion. You take HNO3, you dissolve HNO3 in water, it will give you H plus ion. You take H2SO4, you dissolve H2SO4 in water, it will give you H plus ion, right? You take CH3COOH, we can take organic acids also. You can take benzene, sulfonic acid, right? So whether it is inorganic or organic, right? In both cases, we have acids. So all these compounds from HCl to benzene sulfonic acid, they will give H plus ion in the solution. So according to Arrhenius, we can say that all of these are Arrhenius acid because they are H plus donor. On the other side, Arrhenius also defined base, and how he defined base? In a very similar way. He said that if a compound can donate H plus ion, then it is acid. So on the other side, if an electrolyte is there which can donate OH minus ion, which can donate what? OH minus ion. So if an electrolyte can donate OH minus ion, then it is called as base. For example, if I say sodium hydroxide, if I say iron hydroxide, right? If I say ammonium hydroxide, so I think this point you can observe from the formula also, that if your compound, right, in the formula you have OH group, you have a hydroxyl group, so probably it can give OH minus ion in the solution. And if your compound is able to give OH minus ion in the solution, that means it is a base according to Arrhenius. So Arrhenius concepts of acid and base, H plus donor, OH minus donor, right? H plus donor is acid, OH minus donor is base. I think this point you know from class 10th itself. But point is, this concept was given by Arrhenius, right? But very soon we realized that according to Arrhenius, we cannot classify all the compounds as acid and base. So we need few more concepts of acid and base. So that's why after Arrhenius, we have a concept of Lewis, concept of Bronsted. So one by one, let us see these two also. What is Lewis concept? What is Bronsted concept? But one thing is there, Bronsted concept is much more important for you in this chapter. So out of Arrhenius, Lewis and Bronsted, please focus more on the Bronsted concept, right? So what is the Bronsted concept of acid and base? See, Bronsted said that acid are those compounds which can donate H plus ion in the solution. So you can say that according to Bronsted, the definition of H plus is same as Arrhenius, right? For acid, both have same definition, right? But for base, Bronsted said something else. For base, Bronsted said that bases will accept H plus ion, right? So whatever example I wrote for Arrhenius acid, so same examples I can write for the Bronsted acid, right? Again, HCl, H2SO4, HNO3, hydrogen cyanide, HCN, acetic acid. All these Arrhenius acids are also called as Bronsted acid because Arrhenius, Bronsted have same definition regarding the acid. But in case of base, the definition is different. In case of base, Bronsted says that any compound which has tendency to accept H plus, right, will act as Bronsted base. For example, if you talk about H2O, if you talk about NH3, right, if you talk about organic amines, right, if you talk about organic alcohols. So point is, how these compounds are able to gain or accept H plus. Because if you notice carefully, in these compounds, on the central atom, you have a donatable lone pair. Like when it comes to water, so in water we have oxygen as central atom, it has two lone pairs, and out of two lone pairs, it can share one of its lone pair to H plus. Because when this oxygen will share a lone pair with H plus, then only it will attach H plus. Similarly, in NH3, on the central atom nitrogen, you have a lone pair. So from this lone pair, it can attach the H plus ion. In the amines, on the nitrogen atom again, you have a lone pair, and with this lone pair, H plus can be attached to the nitrogen atom. Similarly, if you talk about alcohol, so in your alcohol, oxygen atom is there, right? And oxygen atom has two lone pair, and one of the lone pair can be shared by H plus, right? So somewhere, when it comes to Bronsted base, you will notice that in the Bronsted base, in the molecule which act as Bronsted base, on the central atom, you will have some lone pair which can be donated to the H plus ion, and that's how it will accept the H plus ion, right? So from today onwards, I hope that you will remember that a compound which can donate H plus is Bronsted acid as well as Arrhenius acid, but the compound which can accept H plus, right, that we define as Bronsted base. But apart from the concept of acid base, in the Bronsted part, we have one more point which is again important, and that is concept of conjugate acid base pair. Concept of conjugate acid base pair, right? See what Bronsted said, that if you have a Bronsted acid, so definitely it will donate H plus. After donating H plus, the anion it will form, that will act as a base, that will act as a Bronsted base, right? And that is called as conjugate base of corresponding acid. So let me tell you that with an example. Suppose if I take HCl, so clearly HCl is acid according to Bronsted, and it can donate what? It can donate H plus ion to form H plus and Cl minus. So point is, if I say that HCl is conjugate acid, if I say that HCl is conjugate acid, then after losing H plus, HCl is converting it into Cl minus anion, right? So this Cl minus anion will be called as conjugate base of your HCl, and overall HCl Cl minus are conjugate acid base pair. HCl Cl minus are conjugate acid base pair, right? More examples we can take. Suppose if I take CS3COOH, right? So it will decompose into CS3COO minus and H plus. So here, if I assume that acetic acid is my conjugate acid, right? I am writing Ca, conjugate acid. So if acetic acid is conjugate acid, then automatically after losing H plus, it is giving you acetate ion, right? So this acetate ion will be the conjugate base. So in this case, I can say that acetic acid and acetate ion are nothing but pair of conjugate acid and conjugate base, right? And similarly, you can also talk in terms of base, right? Suppose if I take NH3, right? NH3 can gain H plus to produce NH4 plus ion, ammonium ion, right? So point is, if NH3 is accepting H plus, then according to Bronsted, NH3 is nothing but base, conjugate base, and after accepting H plus, it is converting into ammonium ion. So here I can say that this ammonium ion is nothing but conjugate acid of that NH3. So here NH3 NH4 plus are nothing but conjugate base conjugate acid pair. So any acid after losing H plus, it converts into conjugate base, and any base after accepting H plus, it converts into its corresponding conjugate acid. So this is the concept of conjugate acid, conjugate base you have. Now sometimes you get a direct question from this, yes, in the NEET examination. Like they will give you a compound and they will ask what is the corresponding conjugate acid of that compound, or what is the corresponding conjugate base of that compound. So that you can do in a very easy manner. Suppose if they give you any compound, and for this compound they ask, tell me what is the conjugate acid of this compound. So for any species, if you want to get its corresponding conjugate acid, just add one H plus ion into it. Like, what is the conjugate acid of Cl minus, right? So to get conjugate acid of Cl minus, you need to add one H plus. So Cl minus plus H plus gives you HCl. So for Cl minus, corresponding conjugate acid is HCl. What is the conjugate acid of H2O, right? So for H2O, if you want to get conjugate acid, one H plus will be added. So H2O plus H plus gives you hydronium ion, H3O plus ion. So for any compound, right, if you want to get its corresponding conjugate acid, just add one H plus. And similarly, from any compound, if you want to get its corresponding conjugate base, just remove one H plus, right? Like, what is the conjugate base of NH3? What is the conjugate base of NH3? So from NH3, if I want to get its conjugate base, I will remove one H plus. And from NH3, if I remove one H plus, it will become what? NH2 minus, right? So NH2 minus is the conjugate base of NH3. So from any compound, if you want to get its conjugate acid, add one H plus. And if you want to get its conjugate base, remove one H plus, right? Also, according to Bronsted, there are certain compounds which can accept as well as donate H plus, right? So they are like amphoteric substance according to Bronsted, right? Some of the common examples are water, right? NH3, right? H2PO4 minus, HSO4 minus. So if you notice, all these species, right, they have either negative charge or lone pair on the central atom. So all of these, they can accept H plus and they can behave like a Bronsted base. At the same time, they also have polar hydrogen. They also can donate H plus ion. So that means they also can behave like Bronsted acid. So these compounds are called amphoteric according to Bronsted, right? So concept of conjugate acid base, how to get conjugate acid base, right? From any compound, what is amphoteric according to Bronsted. These things you should know in the Bronsted concept. One more point is there. In the Bronsted part, especially in the conjugate acid part, right? Whenever you take an strong acid, so for strong acid, its corresponding base will be weaker. So we have a reverse relation here. If conjugate acid is strong, then its conjugate base will be weak. If conjugate acid is weak, then its corresponding conjugate base will be stronger. And same thing is applicable for the base. If you have a weak base, then its corresponding acid will be strong. If you have a strong base, then its corresponding acid will be weaker. So we have a reverse relation here between conjugate acid, conjugate base, right? If conjugate acid is strong, then conjugate base will be weak. We are talking about the strength of acid base, right? Now, after Bronsted, one more concept you have, and that is none other than Lewis concept. Acha, in Lewis concept, we don't have those many points, but from here also sometimes we get direct question in the examination, right? At least from the identification part. First thing is, let's understand what is this Lewis concept. See, according to Lewis, right, the definition of acid base is completely different concept we have in Lewis part, right? Lewis said that any compound, if it has tendency to accept or gain electron, any compound, if it has a tendency to accept or gain electron, then that compound is acidic in nature. That compound is acidic in nature. And if any compound is there which have tendency to donate electron, right, which has tendency to donate electron, right, then that compound is said to be basic in nature. That compound is said to be basic in nature, right? Now here you will be getting questions directly of identification. They will give you certain compounds and they will ask which is Lewis acid, which is Lewis base. Now when you try to identify, it's very easy. Like you must have gone through the chemical bonding chapter, and in your chemical bonding chapter you talk about octet rule, right? And inside octet rule you talk about octet deficient compounds, right, octet precise compounds, and expanded octet compounds. So point is, if you see that you have a compound in which the central atom has incomplete octet. So that means what? If your central atom has incomplete octet and it has some vacant orbital, because vacant orbital is very much necessary. If a molecule has vacant orbital, then only it can gain electron. So if your central atom has incomplete octet, that means it is somewhere electron deficient. So it will try to gain electron. So it will behave as Lewis acid. For example, if you talk about BH3, AlCl3, BF3, right? So all these compounds will behave like Lewis acid, because in these cases the central atom has incomplete octet and the central atom has a vacant orbital, so they can gain electron. So one point is this, in order to identify Lewis acid, that your central atom should have incomplete octet. Another point is there, in the same chemical bonding chapter, you talk about polarity, right? Dipole moment, delta positive, delta negative. So if you write the charges, if you write down the polarity of your molecule, and if you see that your central atom has some delta positive charge on it. So if your central atom has some delta positive charge on it, so definitely delta plus means it will have a tendency to attract negative charge. It will have tendency to attract electron. So in that case also, your central atom or molecule will act as electron accepting species or Lewis acid. For example, right, if I talk about carbon dioxide. So in carbon dioxide, if you notice, here carbon has a complete octet. But according to polarity, the carbon atom has some delta positive charge on it. So because this carbon has some delta positive charge in it, it will try to attract electron. It will behave like Lewis acid. Similarly, if you talk about SO3, Again, in SO3, you have expanded octet, right? But the central atom, sulfur, has some delta positive charge because oxygen is more electronegative. So even this SO3 can behave as Lewis acid. And on the other side, if you try to identify Lewis base, so Lewis base identification is much more easier, right? Draw the dot structure. Of course, dot structure is important here because then only you will be able to understand whether you have an incomplete octet species or what is the polarity. So draw the dot structure. If your central atom has lone pair on it, and that can be donated. So definitely, if your central atom has lone pair and that can be donatable, right? So it will have tendency to donate electron, and then it will act as Lewis base. For example, if you talk about NH3, if you talk about water, if you talk about alcohol, right? Do you people remember nucleophiles in your organic chemistry? Basically, all the nucleophiles you have in your organic chemistry, they are nothing but Lewis bases. And these molecules you must have seen in your organic as nucleophile, right? Ammonia, water, alcohol, ether, right? NO2 minus, cyanide. So these all have tendency to donate electrons. So these all species will act as Lewis base. So in the Lewis part, they will ask question regarding which is Lewis acid, which is Lewis base. So now I think you have understood very well the concept of acid base according to Arrhenius, according to Bronsted, according to Lewis, right? So definitely now it's time to see that from these topics, what type of questions we get in the examination. And see, whenever I am discussing a question, right, please pause the video, do it by your own first, right? And then you match the answer with me. So here we have a question from the concept of acid base itself. And let's see what it says. Conjugate base for the Bronsted acid H2O and HF, right? Just now I told you, right, that they will give you a compound and they will ask what is the corresponding conjugate acid or conjugate base of that. So here they are saying that we have H2O, right? We have H2O, and for H2O they are asking its conjugate base. So for any compound, if I want to get its conjugate base, what I need to do? I need to remove one H plus. So from H2O, if I remove one H plus, I will get OH minus. So for H2O, OH minus is your corresponding conjugate base. And similarly, they are also asking the conjugate base of HF, right? So same like HF, right? For HF, if I want to get the conjugate base, I need to remove one H plus. And from HF, if I remove one H plus, I will get F minus ion. So for H2O, the conjugate base will be OH minus hydroxide ion. And for HF, the conjugate base will be F minus fluoride ion, right? Now see the options. I think the first option itself is your answer, right? OH minus and F minus respectively will be the conjugate base of H2O and HF, right? Right? In the same way, suppose they ask what is the conjugate acid. So for getting the conjugate acid, you need to add H plus. Like for H2O, the conjugate acid will be what? H2O plus H plus means H3O plus. So here definitely your answer is A, of course. And this question from the concept of acid base itself, we got in the NEET 2019 examination. Again, same type of problem you can expect in your exam too, right? Let's see a few more questions from the concept of acid base. Can you answer this? Which of the following, again pause it, do it by your own. Which of the following fluorocompound is most likely to behave as Lewis acid? Just now I told you, okay, not Lewis acid, they are asking about Lewis base. So Lewis base is much easy to figure it out, right? I told you how to identify Lewis acid and Lewis base. If your molecule has incomplete octet for the central atom, or if it has delta positive charge, then it is Lewis acid. If your central atom has donatable lone pair, then it will act as Lewis base. So if you check one by one, the first option is BF3. If I draw the dot structure of BF3, so clearly in BF3, the central atom boron is having a deficiency of octet. So this will act as what? Lewis acid, right? If you check the next option, PF3, so phosphorus has total 5 electron in the valence, and here we have 3 fluorine. Each fluorine will take 1 electron from the phosphorus through covalent bond. Now here, if you notice in PF3, the phosphorus has a lone pair, and phosphorus can extend its valency up to 5, right? So definitely phosphorus can share this lone pair with H+, so it can gain H+. So here PF3 can act as Lewis base as well as Bronsted base, right? Lewis base because PF3 has a lone pair which can be donated, and of course it can be donated to H+, means it can accept H+, so it is also like a Bronsted base. Now for the rest of the option, if you notice in CF4, carbon has 4 fluorine attached to it. Now here you don't have deficiency of octet, but if you check polarity, carbon has delta positive charge. So if your central atom has delta positive charge, then also it will act as Lewis acid. And same for your SiF4. In SiF4, you draw the dot structure, the central atom silicon will have delta positive charge. So SiF4, CF4, BF3, they can behave as Lewis acid, but PF3, because it has a donatable lone pair, right, it will behave as a Lewis base. And also PF3 can act as Bronsted base, because if that lone pair is given to H+, it can accept the H+ ion. So here your answer will be no doubt B. And again, this question we got students in the NEET 2016 examination, right? Now, after understanding the concept of course, acid base, right, according to Arrhenius, Bronsted, Lewis, we know that we are talking about acid and base because we have to discuss about electrolyte in this chapter, and all the acid bases, they are nothing but electrolytes. And please try to memorize some of the strong acids, weak acids, strong base and weak base, like all the inorganic acids like HCl, HNO3, H2SO4, they are strong acids, right? Some of the inorganic acids like H3PO4, HNO3, H2CO3, right? H2CO3, H3PO4, HCN, right? They act as weak acid. And NaOH, calcium hydroxide, potassium hydroxides, they are like strong bases. And organic bases, right? Like RNH4 plus OH minus, right, or NH4OH, inorganic base, they are like weak bases. And when you look into your problems of NEET, especially the PYQ, you will notice that they ask the same acid base again and again. Like in most of the question, you will find either acetic acid, benzoic acid, or HCN as an example of weak acid, and NH4OH or iron hydroxide as example of weak base. So these are some common examples of weak acid, weak base, and that you need to remember, because you need to you should be able to identify which acid is strong, which acid is weak, and which base is strong, which base is weak. Now point is, for electrolytes or for acid base, because acid base are nothing but examples of electrolyte, we have a term called degree of dissociation denoted by alpha, and this term is very important, especially for the weak electrolytes, because you know that weak electrolyte or weak acid, weak base, they always have partial ionization. So point is, suppose I took an electrolyte, right, and I took n moles in total. Means what? I took n moles of an electrolyte and I dissolved that into water to make a solution. Now out of n mole, suppose x moles are getting dissociated. Out of total n moles, suppose x moles of the electrolytes are getting dissociated. So here we define degree of dissociation alpha as amount which gets dissociated, here in this example x mole, divided by total amount of electrolyte that we have taken, that means n. And that is the concept of degree of dissociation. Please remember that, because We have to use degree of dissociation in this chapter so many times. So you need to be very much clear regarding the degree of dissociation. And according to me, it's a very easy topic, very easy point. It's a kind of answer of many questions to us. What is degree of dissociation? How much electrolyte is getting dissociated divided by how much total electrolyte we have taken, right? And if you talk about separately for strong and weak electrolyte, so please focus here. If you take strong electrolyte, you know that strong electrolytes, they are completely dissociated, they are completely ionized. So if this electrolyte is strong and I take n moles, then the whole n mole will dissociate. So then the dissociated amount will be n, total amount will be n by n will be 1. So I can say that when we have a strong electrolyte, so for strong electrolyte, the degree of dissociation is 1, right? But when you take a weak electrolyte, so for weak electrolyte, right, this x will be 100% smaller than n, because out of n, some part will ionize. And if x is small, n is large, so this alpha will be 100% less than 1. So for weak electrolyte, your alpha has a range. It ranges from 0 to 1. You will see in your questions the values of alpha as 0.01, 0.02, 0.1, 0.4, like this. So for weak electrolyte, degree of dissociation ranges from 0 to 1, and for strong electrolyte, the degree of dissociation is directly equals to 1, right? So you can say that in terms of degree of dissociation also, we can explain the meaning of strong and weak electrolyte. And I think somewhere both the points are connected, right? When you say strong electrolyte, degree of dissociation is alpha, alpha is 1, degree of dissociation is 1. Why it is 1? Because whatever amount I take, the whole amount will dissociate, right? And similarly for weak electrolyte, the alpha is always 0 to 1 or always less than 1, right? Why? Because whatever amount I take for weak electrolyte, out of that the whole amount will not break, only some part will break, right? So x will be always smaller than n. So I hope you have understood at least what is degree of dissociation. That means amount dissociated divided by total amount of electrolyte taken, right? Now, just after degree of dissociation, we will have to talk about the dissociation constant. Let me make it a little bit easier to you. Hey, all of you, please listen, please listen. You must have gone through chemical equilibrium chapter, right? And in your chemical equilibrium chapter, you must have calculated the equilibrium constant in terms of concentration, Kc. And how you calculate Kc? Kc is concentration of product divided by concentration of reactant raised to the power stoichiometric coefficient. Students, point is, when we say dissociation constant, so they are same as your equilibrium constant. The way you calculate Kc, in the same way you calculate dissociation constant or ionization constant. The only difference is Kc we use in chemical equilibrium, and the same Kc kind of we have changed the name. Concept is same, but we have just changed the name. In ionic equilibrium, we call it ionization or dissociation constant. So point is, dissociation or ionization constant is also calculated in the same way. If you have an equation of equilibrium, so concentration of product divided by reactant raised to the power stoichiometric coefficient, right? And in this chapter, what we do? We define different types of dissociation constant, right? Just to understand for what compound we are talking about. Like in general, you will notice that in general, we call dissociation constant, or we represent dissociation constant by K, simple K, right? But when you calculate dissociation constant of any acid, so there we represent that by Ka. A stands for acid. When we calculate it for base, so then it is called Kb, dissociation constant of base. When we calculate that for water, then it is called as Kw. So whether it is K, whether it is Ka, whether it is Kb, whether it is Kw, all are same, all are dissociation constant. Moreover, all are equilibrium constant only. All the K, Ka, Kb, Kw are calculated as concentration of product upon reactant power stoichiometric coefficient, right? So one by one, Let's see these dissociation constant, right, with some example. Like first of all, suppose if I take an electrolyte in general. In general, if I take an electrolyte, something like AXBY. Suppose this AXBY electrolyte, it is decomposing as XA Y plus cation and Y B X minus anion, right? So this is the dissociation of any weak electrolyte in general, right? So here, if I calculate the dissociation constant or equilibrium constant, right? We have just changed the name, the concept is same. Here you are calling it dissociation constant. The same thing in your chemical equilibrium, you call it as equilibrium constant, right? So here for this reaction, if I calculate the dissociation constant, so that will be concentration of ion A power its coefficient X into concentration of ion Y, not Y, sorry, concentration of ion B power its coefficient Y divided by concentration of the electrolyte power coefficient 1. Isn't it same? When you calculate equilibrium constant, so there also you say concentration of product upon reactant raised to the power coefficient. And when you are calculating dissociation constant, so here also you do the same thing, concentration of product upon reactant raised to the power stoichiometric coefficient. So in general, for any electrolyte, we call it what? Dissociation or ionization constant. But the same thing, if you calculate for acid, it is called Ka. When you calculate for base, it is called Kb. And for water, it is called Kw, right? Let me give you some examples for them also, right? For acid, right? You take a weak acid, any weak acid, like the most famous one is CS3COOH. So we know that in your solution, the acetic acid will decompose as CS3COO minus and H plus. So for this weak acid, if I write down the dissociation constant, so it will be Ka. And here we are just writing the expression, of course. So concentration of acetate ion power 1 into concentration of H plus ion power 1 divided by concentration of acetic acid molecules power 1. So this is the expression for dissociation constant of acid. You take any weak acid, right? For that you represent it by Ka. Similarly, if you take a weak base, like suppose I am taking ammonia. When you dissolve NH3 in water, right, it ionizes to give you NH4 plus ion and OH minus ion. So now here, because NH3 is base, its dissociation constant will be Kb. And again, Kb will be what? Concentration of products, means concentration of ammonium ion power 1, OH minus ion power 1 divided by concentration of your reactants NH3 power 1, and water you can skip because this thing you know from your chemical equilibrium chapter only, that when we have a pure solid or pure liquid, we put its concentration unity, right? So because H2O is a pure liquid here, we can skip that part because it will become unity in the expression of Kb. So K is what? K is dissociation constant of acid and Kb is what? Dissociation constant of base, right? In the same way, we have another term that is Kw, which is called dissociation constant of water, right? Water dissociation you can write in two ways. One is this, H2O will decompose as H plus and OH minus, right? But as compared to that, the better form is H2O plus H2O gives you H3O plus and OH minus. Both are same equation, both are dissociation of water, but the difference is this is preferred. Why? Because if you write like this, H2O decomposes into H plus and OH minus. So in your solution, OH minus is a stable ion, but H plus, right, it will not exist, it is unstable. H plus will automatically combine with H2O. So that's why this form of dissociation of water is preferred as compared to this. But when you are solving question, right, then you can use any of these two. It will not give you a bad result or it will not give you any kind of error in your calculation. But point is, For water or for ionization of water, if I write the dissociation constant, so that will be called as Kw, right? And here Kw is what? Concentration of products, means H3O plus power 1, OH minus power 1 upon concentration of reactant. Again, your reactant is pure liquid, so you can skip that. So from this equation, the Kw is concentration of hydronium ion into OH minus ion. And from this expression, if you calculate Kw, right? So it will be concentration of H plus power 1, concentration of OH minus power 1. Now why I am writing these two? Because I don't want you to get confused. You can write Kw as this, hydronium into OH minus. At the same time, you can also write Kw like this, concentration of H plus into OH minus. But the most important point here is, you know that whether it is equilibrium constant or whether it is dissociation constant, they are temperature dependent. They are temperature dependent. So if your temperature is constant, you will have a fixed value of dissociation constant or equilibrium constant. Now, not for those acids and bases, but at least for water, you need to remember its dissociation constant at 25 degrees C. Students, at 25 degrees Celsius, or which you can say as 298 Kelvin. So at 25 degrees C or 298 Kelvin, the dissociation constant of water has a fixed value which is 10 to the power minus 14. Please remember that always throughout the chapter. And if at 25 degrees C, the Kw is 10 to the power minus 14, that means what? That means concentration of H plus into OH minus will be 10 to the power minus 14 at 25 degrees C. Correct? So at least the dissociation constant of water you need to remember always for this chapter. Now, apart from this Kw that is equals to 10 to the power minus 14, one more thing is there, like which you should know regarding the dissociation constant, and it is about the conjugate acid and base pair. Right? We saw what is conjugate acid base like in the Bronsted concept. But point is, when you talk about conjugate acid and its base pair, so we have a relation between the dissociation constant of conjugate acid and conjugate base. Point is, let's take an example. Let's say that when CH3COOH dissociates or decomposes into CH3COO minus and H plus. So basically this is your acid, this is your weak acid, right? And for this acid, your acetate ion is nothing but your conjugate base. Now point is, from this reaction if I write the dissociation constant, so that will be for your acid, and the dissociation constant Ka can be written here as concentration of acetate ion into concentration of H plus ion divided by concentration of acetic acid. So this is the expression of dissociation constant of acid, that is acetic acid. Now, for the same acid, if I consider its conjugate base, that means CH3COO minus. So you know that if CH3COO minus is a base according to Bronsted, so it can gain H plus from water to produce CH3COOH along with some OH minus ion. Now in this equation, this is my base. This is my Bronsted base, and for this base or this dissociation of base, if I write the dissociation constant, so here I will say Kb, right? Kb is for your acetate ion and Ka was for your acid, right? Now the expression of Kb will be concentration of acetic acid into concentration of OH minus divided by concentration of your acetate ion, and again water, because it's a pure liquid, you can put unity, right? So here the dissociation constant of conjugate acid is this and the dissociation constant of conjugate base is this. Now if you see the expression carefully and if you try to calculate Ka times Kb, so if you multiply dissociation constant of conjugate acid with dissociation constant of conjugate base, if you multiply the RHS term, if you notice, right, when you will be multiplying, acetic acid concentration will be cancelled, acetate ion concentration will be cancelled, you are left with only concentration of H plus into concentration of OH minus. And just now we saw that when we have a concentration of H plus into OH minus, so that is nothing but Kw. So that's a relation we have, and sometimes we do get a direct question from this. Relation is dissociation constants of conjugate acid into conjugate base is equals to Kw, and you know that at 25 degrees C it will be equals to 10 to the power minus 14. So please note it down, please remember this formula, because sometimes you will be getting question like for a acid, for a conjugate acid, Ka will be given, you will have to find Kb, or sometimes Kb will be given, you have to find Ka. Now to do that, K will be equals to 10 to the power minus 14 upon Kb, or Kb will be equals to 10 to the power minus 14 upon Ka, right? So this is the relation we have between Ka and Kb for conjugate acid base pair, right? Now one more point regarding this chapter. In this chapter you will notice terms like pKa, pKb, right? So you know, when we do calculation of pH, when we talk about calculation of pH, so we have to deal with lots of log terms. So what we have done, we have made some notations, we have made some representation for the log terms, and those terms you need to understand. Like whenever you see in your chapter pKa, so you need to understand pKa is written for minus log Ka. So basically whenever I get this expression minus log Ka, so it can be represented as pKa. Similarly, if I see this term pKb, so as soon as I see pKb, I can understand that pKb stands for minus log of Kb, right? Similarly, if I see pKw, so I need to understand that it is nothing but minus log Kw. So when you do certain calculation, you get log expressions. So in those log expressions, whenever you find that I have somewhere minus log Kw, so minus log Kw can be written as pKw, minus log Kb can be written as pKb, minus log Ka can be written as pKa, right? These terms are important for you, correct? Not only that, in the same way, you can say that, although we are going to talk about pH scale, but in the same way you can say that pH is nothing but minus log activity or concentration of H plus. pOH is nothing but minus log activity of OH minus. And just for memorization purpose, you can apply a trick here. You can say like this, whatever comes in the power of P here, that goes right inside minus of log, means P of OH, so this OH will be inside minus of log, minus log of OH minus. Here P power is H, so minus log concentration of H plus. P power Kw, so minus log of Kw. P power Kb means minus log Kb. So just for your memorization purpose, you can use this trick, right? But these terms you need to understand, because you will have to interchange. Sometimes in your calculation you will get this minus log Kb and you will have to rewrite it as pKb. Or sometimes you get pKb and you will have to expand that pKb as minus log Kb. So in these conversions, right, of pKa, pKb into minus log Ka, minus log Kb, you need to be very strong, right? And that's how you can improve your calculation, correct? So now after talking about all the dissociation constants, like what is Kw, what is Ka, what is Kb, what is K, right? Let's have an very important relation which is used very often in this chapter at many places. This is Ostwald dilution law. So first of all, let me tell you why we have this law. So you know that we talk about weak electrolyte in this chapter, and weak electrolytes are always partially ionized. Weak electrolytes are always partially dissociated. So point is, for weak electrolyte, we have the term alpha, that means degree of dissociation. And alpha tells you that up to what extent your weak electrolyte will decompose, right? If more alpha is there, if the higher value of alpha is there, that means you will understand that your weak electrolyte is more dissociating. It is having more and more dissociation. Higher the alpha, more is the dissociation. Now point is, there will be certain factors on which alpha will depend. Like one factor is temperature. If you increase temperature, right, the alpha or extent of dissociation will increase. So there can be different factors on which the degree of dissociation will depend. Temperature is one of them. Now one factor is concentration. Students, point is, for any weak electrolyte, for any weak electrolyte, when you increase its concentration, so due to increase in concentration, always the alpha will decrease. Means you take a weak electrolyte, you prepare a solution. Now in your solution, if you increase the concentration of electrolyte, so by increase in concentration of electrolyte, the degree of dissociation will decrease. Means more the concentration, lesser is the dissociation, right? And you can say the same thing in other way, like if you talk about dilution. So dilution means what? Dilution means increasing the amount of solvent, right? Increasing the amount of water without changing the amount of solute. So if you do dilution, right? If you do dilution, so with dilution the concentration will decrease, and if concentration will decrease, in that case the degree of dissociation will increase. So that's the overall logic of Ostwald dilution law we have, right? Ostwald dilution law means with dilution the degree of dissociation of weak electrolyte will increase. With dilution you will have more and more dissociation. Now the same law, the same logical, the same conceptual law we can also explain mathematically, right, with some formulas. How? Let me tell you. Suppose if I have a weak electrolyte like this, CS3COOH. Of course, I hope you know that acetic acid, it has a N factor of 1. When it will decompose per molecule, it will give you 1 H plus ion. So this acetic acid, when it will decompose, it will give you CS3COO minus ion, right, and H plus ion. Now point is, let's assume that initially before dissociation, the concentration of acetic acid was C. So before dissociation, there will be no ion by default. So the concentration of ions will be 0. Now here, if I assume that the degree of dissociation of acetic acid is alpha, right? So after dissociation, with help of alpha, I can calculate what will be the amount, what will be the concentration of acetic acid and ions. Because I told you, degree of dissociation can tell you that how much amount is getting dissociated, right? And it is very simple, right? With your initial amount, multiply the degree of dissociation, so that is your dissociated amount. Here, if initial concentration is C and degree of dissociation of acetic acid is alpha, then the dissociated amount will be C into alpha. So C into alpha part of your acetic acid will decompose. Now after, initially it was C alpha part will decompose. So after decomposition, after dissociation, the acetic acid will remain C minus C alpha. And now again, if you apply stoichiometry, you can say like this: 1 mole of acetic acid can produce 1 mole of acetate ion, 1 mole of H plus ion. So by the dissociation of C alpha part of acetic acid, I will get C alpha part of acetate ion and C alpha part of H plus ion, right? This is in general, right? For that electrolyte whose N factor is 1, for that weak electrolyte whose N factor is 1. Now here, if you calculate the dissociation constant, right? Of course, because it is weak acid, I can write K, but here I am creating a general formula. So let me write it simply, dissociation constant K. Now that will be equals to concentration of product upon reactant raised to the power stoichiometric coefficient. So after dissociation, concentration of acetate ion is C alpha, so C alpha power 1 into concentration of H plus ion is also C alpha, so C alpha power 1 divided by concentration of acetic acid is C minus C alpha, which can be written like C into 1 minus alpha. Now here if you notice, some of the terms will be cancelled, right? I think 1C will be cancelled. And also, if you have a weak electrolyte whose degree of dissociation is very much smaller, right? So if alpha is very much smaller, right? If alpha is very much smaller as compared to 1, then what we can do, out of 1 minus alpha, we can ignore this alpha, because if there are two numbers, one is very large, one is very small, then the small number can be neglected in case of addition and subtraction. So out of 1 minus alpha, if alpha is very small as compared to 1, so alpha will be ignored and it will be simply 1. So K will be equals to alpha into C alpha, which is C alpha square. And from here, if you calculate alpha, so that will come out under root of K by C. So mathematically, when alpha is very small for weak electrolyte, you can say that degree of dissociation will be equals to under root of K by C, under root of dissociation constant upon concentration. Now from this mathematical relation also, you can obtain the same result of Ostwald dilution law. Here, if you increase C, if you increase the concentration, so because concentration is in denominator, so by increase in concentration, the alpha will decrease. And that's what I said initially, that for weak electrolyte, when you increase concentration, the alpha will decrease. Right? When you increase concentration, the alpha will decrease. So this is Ostwald dilution law, but this formula itself, that is alpha equals to under root of K by C, is very important for you. Right? So please remember, right, this formula throughout the chapter, because multiple times you will require this formula, that is alpha equals to under root of K by C. So that's it about the Ostwald dilution law, how concentration affects the degree of dissociation of weak electrolyte. Now, can we do some question from the concepts of dissociation constant and especially that Ostwald dilution law? Pause the video again if you want to do it by your own, and later on you can check the answer. I hope the question is pretty much visible to you. Question is the percentage of pyridine. So pyridine, you know that it's a organic base, but organic bases are mostly weak bases, right? So percentage of pyridine, which is a weak base that forms pyridinium ion, right, after absorbing H plus in a 0.1 molar aqueous pyridine solution, and Kb for pyridine is given 1.7 into 10 power minus 9. So if you read the question carefully, they are asking about the percentage of pyridine that forms pyridinium ion, right? Means what? They are basically asking about percentage dissociation. Students, when you calculate degree of dissociation, which is alpha, and if you multiply alpha with 100, so that tells you about the percentage dissociation. So alpha is degree of dissociation, but alpha into 100 is nothing but percentage dissociation. So in this case, first thing is we have to calculate alpha, we have to calculate degree of dissociation. And what are given things? First point is we have a weak base solution. We have a weak base solution. For that weak base, we have the value of Kb, we have the value of concentration. So we can directly apply the formula of Ostwald dilution law, that is alpha equals under root of K by C. That's the general formula. But in case of base, I can say weak base, I can say alpha equals to under root of Kb by C. Now here alpha I have to calculate. Kb is given in the question itself. It is 1.7 into 10 to the power minus 9 divided by concentration of the weak base is 0.1, right? So to remove 0.1, you can multiply with 10 in the denominator and with 10 in the numerator. So it will come out under root of 1.7 into 10 power minus 8. Now if you do square root, alpha will be nearly square root of 1.7, square root of 1.7 into square root of 10 to the power minus 8 is very easy. It will be 10 to the power minus 4. But we have to calculate percentage dissociation. So percentage dissociation will be this into 100, means under root of 1.7 into 10 to the power minus 4 into 100, it will come out 10 to the power minus 2. Now if you calculate, square root of 1.7 will be 1 point something, like 1.2 or 1.3 nearly if you calculate. And if you do 10 power minus 2 here, so it will be nearly 0.012 or 13. The nearest answer is B. Of course, it should be B. So basically, if you find the square root of 1.7, that will come near about 1.3, right? And 1.3 into 10 power minus 2 can be written as 0.013%, right? So you can calculate alpha from dissociation constant and concentration, and from alpha you can find what? You can find percentage dissociation. And of course, for this question, the answer will be B, which is your answer. And point is, directly from Ostwald dilution law, we got question in the NEET 2016 examination, correct? So now I think these types of problem you can solve easily, correct? So, talking about dissociation constant, there is a topic which most of the time we forget to learn, right? But now we can't skip that. Point is, we have concept of polyprotic acid. First of all, what is the meaning of polyprotic acid, students? Those acids, right, whose N factor is greater than 1, right? If you have an acid and per molecule from that acid you can obtain 2 or 3 H plus ions. So definitely its N factor will be 2 or 3. And that type of acid is called as polyprotic acid. Poly means many, protic means proton. So if one molecule of acid can give you many protons, so that is called polyprotic acid. Now point is, for polyprotic acid, right, dissociation constant is calculated step by step, step by step. Like if I take a very famous example, let's say H2SO4, right? H2SO4 is diprotic. So H2SO4 will ionize not directly as 2H plus and sulfate. It will ionize step by step. In the first step, it will lose one of its H plus and the remaining part will be HSO4 minus, right? In the second step, the HSO4 minus part will further lose one more H plus and finally it will convert into sulfate ion. So point is, H2SO4 will ionize in 2 steps, and for both the steps the dissociation constant will be different, right? Like here in the first step, let's say that dissociation constant is K because it is acid, so A1. So in the second step the dissociation constant will be different, let us say it is Ka2, and more precisely, step by step its dissociation constant will decrease. Here you will see that Ka1 is greater than Ka2, is greater than Ka3 for triprotic acid, and so on, Ka4 for tetraprotic acid. Point is, H2SO4 is a strong acid as compared to HSO4 minus, because you can see clearly that H2SO4 is neutral while HSO4 has a negative charge. So removal of H plus will be easier from the neutral species as compared to that species which has negative charge, right? So with multiple time dissociation, the acidic strength will gradually decrease, right? So as compared to H2SO4, HSO4 minus is weaker acid, and if HSO4 minus is weaker acid, it will have low dissociation constant, and if H2SO4 is stronger acid, so it will have higher dissociation constant. So Ka1 will be definitely greater than Ka2, right? Same concept you can apply for the other polyprotic acids like H2CO3 or H3PO4 or H3PO3, right? But point is, you should have certain idea about the dissociation of polyprotic acid. The main thing is, polyprotic acids, they always ionize step by step, step by step. And if I write the overall ionization equation, right, I can do that simply by adding these two. If I add these two equations, so I will get this sort of equation. H2SO4 converts to twice of H plus. When you will be adding HSO4 minus in the product, reactant will be cancelled. So you are left with sulfate. So point is, now for this overall dissociation, the dissociation constant will be different from these two. Let's say it is K. So this K will be equals to multiplication of these two, K1 into K2. If you remember, the relation between dissociation constant or equilibrium constant, you do learn in your chemical equilibrium chapter. In your chemical equilibrium, if you notice, right? So if I have two equations and their equilibrium constants I know, so by adding these two equations, whatever equation I get, so for that equilibrium constants are calculated by multiplying the individual equilibrium constant. So same thing we are using for the dissociation constant. So for the first one, second one, the dissociation constants are K1, K2. And when I'm adding these two, so for my final equation, the dissociation constant will be K1 into K2. So these concepts you should know regarding your polyprotic acid, correct? Now, moving ahead, can we have a question? And if you look at this problem, it looks like it's a question from your polyprotic acid itself, right? Phosphoric acid. The formula of phosphoric acid, I think it's very common, H3PO4. So phosphoric acid, please pause it, do it by your own, later on match the answer. So phosphoric acid ionizes in 3 steps, we know that, with their ionization constant values K1, K2, K3. So in the first step, ionization constant is K1, second step K2, third step K3 respectively, while K is the overall ionization constant. Okay, then choose the correct answers from the options given below. So they are asking that which points are correct here. First point is log K equals log, okay. If overall dissociation constant is K, so it can be written as K1 into K2 into K3. We saw that on the previous slide, right? Now point is, if I take log on both sides, so left hand side will be log K and right hand side will be log K1 into K2 into K3. And I hope you people know the basic formula of log, right? Inside log, whenever two numbers are there in multiplication, so that can be expanded in terms of addition. So log K into K2 into K3 can be written as log of Ka1 plus log of Ka2 plus log of Ka3. Now this is what they have written in the A point. Log K equals log K1 plus log K2 plus log K3. So A is absolutely correct, right? Now, if you check B, so in B they are saying H3PO4 is stronger acid than H2PO4 minus. Of course, by the ionization of H3PO4, when H3PO4 will ionize, so in the very first step, you will get H plus ion, and along with that you will get H2PO4 minus. So as compared to H3PO4, H2PO4 minus will be a weaker acid because H2PO4 minus has negative charge, H3PO4 is neutral. So even the point B is absolutely correct. If you check C point, so K1 is greater than K2, so it is directly related with the point B, right? Because H3PO4 is a stronger acid than H2PO4 minus, then H2PO4 minus is a stronger acid than HPO4 2 minus. So K1, it is for H3PO4, K2, it is for H2PO4 minus dissociation, and K3 will be the dissociation of HPO4 2 minus. So K1 will be greater than K2 than K3, right? Last point is K1 is the average of K3 and K2. It's not necessarily true, right? So the only correct point here it will be A, B and C, and A, B, C are there in option B. So definitely in this case your answer should be B, and I hope that most of you have done this question, because just before this question I told you the concept of polyprotic acid. So in this case, of course, your answer will be B, of course it is. And students, this question we got in the NEET 2025 examination, right? So this is what you get in your NEET exam. Now, moving ahead, let's talk about the major part of the chapter. You know very well that almost 50% topic in the chapter is regarding the pH calculation. So we will talk about pH calculation, but first point is, I hope you know about pH scale from your class 10th itself, right? pH scale, which tells you about the acidic or basic nature of a solution, right? By the calculation of pH value. First point is you calculate the pH of a solution as minus log concentration of H plus or hydronium ion, right? Sometimes instead of pH, you calculate POH as a minus log concentration of OH minus. Then you have your pH scale, which says that it's a range from 0 to 14. At 7, you say that your solution is neutral. Before 7, it is acidic. And after 7, it is basic. This is your pH scale. But point is, how we got this pH scale? How we have obtained this pH scale? So your answer is dissociation of water. Students, please remember that your pH scale is completely dependent on water, dissociation of water, ionization of water, right? We talked about Kw, we talked about dissociation constant of water, and we have seen already that the dissociation constant of water is By expression, it is concentration of H plus and concentration of OH minus, right? And when we talk about temperature 25 degrees C, so at 25 degrees C, the Kw is nothing but 10 to the power minus 14. Now this should be equals to concentration of H plus into concentration of OH minus power 1. Now from here, because during the ionization of pure water, we have equal concentration of H plus and OH minus, right? So from here, I can obtain that concentration of pure water, concentration of H plus in pure water is 10 to the power minus 7 at 25 degrees C, right? Now, point is, because water, pure water is neutral, and at 25 degrees C, for pure water, we are getting pH H plus as 10 power minus 7. Later on, if you calculate its pH, so pH will come out 7. So because water is neutral and at 25 degrees C, the pH of water is 7, that's the reason we say that at 7 pH, your solution will be neutral, right? And the Kw, the power of Kw, that is 14, tells you the range of your pH scale from 0 to 14. So point is, if I change the temperature, from 25 degrees C, then the Kw will change. If Kw will change, the concentration of H plus will change, the pH of water will change, then the whole pH scale will shift, right? Suppose that at some higher temperature, like at some 50 degrees C, right? I got my Kw as 10 power minus 12 because with high temperature, the Kw will increase. So suppose, for example, at 50 degrees C, I got Kw as 10 to the power minus 12. So in this case, if you calculate concentration of H plus, it will come out 10 power minus 6. So here pH of pure water will be 6. So in this case, the pH scale will change. It will be something like 0 to, what is the power of Kw? 12. So 0 to 12, and in between 6 will be neutral. So here your pH scale will be like from 0 to 6 acidic, at 6 neutral, and from 6 to 12 basic. Correct? So please remember that the pH scale that we use is at 25 degrees C. But do not worry. In your questions, right, generally most of the time they will use this pH scale for your questions, right? So most of the time you people will be getting question at 25 degrees Celsius. But I think at least this much point you need to understand that pH scale depends on ionization of water. pH scale is created on the basis of ionization of water. So point is, now after understanding in detail what is pH scale and how your pH scale is formed, right, from the ionization of water, now let's talk about the pH calculation, and from pH calculation, what type of questions we get in the examination. Students, please note it down that in the pH calculation part, right, you have subparts, right? Like pH calculation is there for different types of solution. And whenever you solve a question of pH calculation, first try to identify that from which part you have got the question, like whether you have got a question from the pH calculation of a simple strong acid solution or a simple strong base solution, or a mixture of a strong acid with strong acid, or strong base with strong base, or mixture of strong acid, strong base, or whether it is a simple weak acid, or whether you have to calculate a pH of salt or buffer. So for what type of solution you have to calculate the pH, first try to identify the nature of solution, and then according to that you can calculate pH. So we will talk here case by case, and our first case of pH calculation will be when we have a solution of one means exactly one, right? One strong acid or one strong base solution. Like for example, suppose I have a solution of HCl, which is a strong acid, right? Whose concentration is 0.01, right? And for this solution, I have to calculate pH. So it's a simple strong acid, right? It's not a mixture. It's a pure, simple, strong acid whose concentration is 0.01 molar, and we have to get the pH. So in these cases, in case of strong acid solution, how to calculate pH is very easy, right? First, from this acid, you can calculate how much H plus you can obtain, because you know that HCl is a strong acid. So no need of alpha here. Whatever amount is there, it will completely ionize. And one part of HCl can produce one part of H plus. So 0.01 molar HCl will give you 0.01 molar H plus ion. Now once you have obtained the concentration of H plus ion, from that you can find the pH. Here pH will be minus log concentration of H plus, and concentration of H plus is nothing but 0.01. You can write 0.01 as 10 power minus 2, right? And I hope you know that log m power n, so we take power outside. So log 10 power minus 2 will be outside. It will be minus of minus 2 log 10. And some of the log values you need to remember, like log 10, log 2, log 3, log 1. Log 10 is 1, log 1 is 0, log 2 is 0.3010, right? Log 3 is 0.477 roughly. So log 10 is 1 and minus minus plus, so the pH will be 2. So point is, for one strong acid solution, if you have to get pH, right, from your acid, get the concentration of H plus, apply the formula pH equals minus log H plus, get the pH value. Similarly, instead of a strong acid, suppose if you have a solution of strong base, right, something like let's say I have a 0.1 molar solution of NaOH. So you know very well that NaOH is a strong base, right? So here also just dissociate, but in this case, in case of strong base, instead of H plus, you can obtain the concentration of OH minus. So your NaOH will decompose completely into Na plus and OH minus, and because NaOH is a strong base, it will completely ionize. So the whole 0.1 molar will ionize, right? And when 0.1 molar of NaOH will ionize, it will give you 0.1 molar of Na plus and 0.1 molar of OH minus. So here we got the concentration of OH minus as 0.1. So from the concentration of OH minus, you can find POH first. POH will be minus log concentration of OH minus, which is 0.1. Again, same story. 0.1 can be written as 10 power minus 1. Minus 1 will be taken outside. So minus into minus 1 is 1. Log 10 is 1. So the POH will be 1 here. But we have not got the pH. Sometimes students do mistake here, right? Don't do that. This one is not pH. This is POH. Now, from POH, you can find pH as 14 minus of POH. That means 14 minus 1, it will be 13 here, right? So if it is a strong acid solution, find H plus, apply pH equals to minus log H plus. If it's a solution of a strong base, right, find OH minus, right, find POH from minus log OH minus concentration, and then pH equals to 14 minus POH. And like this, you can find pH of either a strong acid solution or strong base solution. But there is a point which you need to keep in your mind again. Sometimes what will happen, the concentration of acid or base in the question, it will be less than 10 to the power minus 5. So please remember, whenever your acid or base, strong acid or strong base, concentration is 10 to the power minus 5. So automatically in that case, the concentration of H plus or OH minus you will be getting, it will be also less than 10 to the power minus 5. So in those cases, you will have to consider the H plus and OH minus from the water itself. If the concentration of acid base, strong acid base is more than 10 to the power minus 5, then no worries. Do the calculation like this. From your acid base, get the H plus OH minus, find the pH POH. But if your concentration of acid base is less than 10 to the power minus 5, then in that case, you will have to add concentration of H plus or OH minus from water while calculating pH. Let me give you an example for that also. Let's say that I have a solution of 10 to the power minus 6 molar HCl. So here you can notice that 10 to the power minus 6 is smaller than 10 to the power minus 5. So HCl will ionize into H plus and Cl minus. From 10 to the power minus 6 molar HCl, the amount of H plus I will get, it will be 10 to the power minus 6 molar. But point is, in water, we have 10 to the power minus 7 concentration of H plus ion. So that concentration we will have to add here. So the total concentration of H plus will be, from acid we are getting 10 to the power minus 6, and from water we are getting 10 to the power minus 7. So you need to add these two, right? Concentration of H plus from water, we have to add it here. Then of course, later on you can do the calculation. If you take 10 to the power minus 7 as common, so it will come out 11 into 10 to the power minus 7, right? 11 into 10 to the power minus 7. And then you can apply the formula pH equals to minus log H plus. So this condition you need to remember, right? For strong acid or strong base solution, if the concentration of acid base is less than 10 to the power minus 5, then you will have to consider H plus and OH minus from the water also. Correct? Now, after strong acid, strong base, right? Sometimes we do get question of mixture of these strong acids and strong base. And please remember, currently I am not talking about weak acid, weak base. Currently we are dealing with only the strong components, strong acid or strong base. So previously we saw that if I have one strong acid or one strong base solution, how we can get the pH. Now point is, sometimes we can have mixture. And when you talk about mixture, so in the mixture part you can have three cases. One is strong acid can be mixed with strong acid, right? Second case, strong base can be mixed with a strong base. And third possibility, strong acid can be mixed with a strong base, right? So now point is, when two strong acids are mixed together, and for the final mixture, if you have to calculate the pH, in this case, right, use the concept of concentration terms. Use the mole concept chapter here, please. Right? In mole concept chapter, I think you must have learned those formula, right? That if you mix two solution of same nature, same acid, same base, right? So in that case, the normality of final mixture is N1V1 plus N2V2 upon total volume, right? So that formula you can use here, right, to do the calculation easily, right? Suppose I have two strong acid. For the first strong acid, the normality volume are N1 and V1. For the second strong acid, the normality volume are N2V2. In your question, instead of normality, if they have given molarity, so you can find normality from molarity, because you know very well that normality is molarity into N factor, right? And for acid, N factor is number of H plus ion per molecule, and for base, number of OH minus ion per molecule. So if you have normality volume of both the strong acids, so here you can directly find pH by applying this formula, minus log N1V1 plus N2V2 divided by total volume. In this case, total volume will be V1 plus V2, but sometimes they further do dilution. So in that case, you will have to see the final volume, right? So minus log N1V1 plus N2V2 upon total volume can give you the pH in case of mixture of strong acid, strong acid. And I hope that logically you are understanding here that when I say N1V1 plus N2V2, so this is the total equivalent of H plus ion upon volume. And total equivalent of H plus ion, right, is also equals to total moles of H plus ion, because H plus ion has an factor of 1. And total moles of H plus upon total volume is nothing but molarity of H plus. Same concept you can apply when you have a mixture of two strong bases. But here, you know that from base you get OH minus ion. So same formula will be there for strong base, minus log N1V1 plus N2V2 upon total volume. Same formula, N1V1 is the normality volume of the first base, N2V2 is the normality volume of the second base. But the only thing is, from the same formula, in this case, you will get POH first. So here we were getting pH. In case of strong base, we will be getting what? POH, right? So these two you can do. But when you mix strong acid with strong base, right? So it's a different case. Why? Because when two acids or two bases are mixed, right, there is no reaction. But as soon as you mix acid with base, there will be neutralization reaction. And in that case, neutralization will happen, and whatever left over, whether your acid is left or whether your base is left, so that will determine the pH of the solution. So in this case, let me talk it separately. Let me talk about strong acid, strong base separately. When you mix a strong acid with a strong base, so there, first you calculate the equivalents. It's my suggestion. You have your molarity, you will have your volume. That will be always given in your question. So from molarity volume, you can find normality first from molarity, and then normality into volume will give you what? Equivalent. So in this case, whenever acid base are mixed, first you calculate equivalents of acid and equivalents of base. And how you get equivalent? Equivalence is molarity into n factor into volume in liter. If you keep your volume in ml, then you will get milli equivalent. Milli equivalent will be molarity into n factor into volume in ml. So according to question, whatever you wish you can do. But first you calculate equivalents of acid and base. Now compare, because you have calculated, you have the magnitude of a gram equivalent of acid base. Now compare. If you see that equivalent of acid is more than base, that means what? That means here after reaction acid will remain. In that case, your solution, final solution will be acidic, because acid is more. And in that case, the pH can be simply calculated as minus log equivalents of acid minus equivalents of base divided by total volume. Done. No need to do anything else, right? Similarly, if you see that equivalent of base is more than equivalent of acid, so in that case, because base is more, so after neutralization base will remain, base is in excess. So after reaction for the mixture, the final mixture will be automatically basic in nature, right? And in that case, again you will apply the same formula, minus log, this time equivalents of base minus equivalents of acid divided by total volume. Of course, we did base minus acid because here base is more, right? So similar formula we are using. Here equivalents of acid minus base, here equivalents of base minus acid. The only difference is here we were getting pH, but again this time here you will be getting what? POH, because base is excess, first base gives you OH minus, right? And finally, there can be the third case when equivalents of acid will be equals to equivalents of base. No need to calculate in this, because if equivalents of acid and base, they are equal, you know that there will be perfect neutralization, right? Both acid base will be completely consumed. So the final solution will be neutral in nature. And if your final solution is neutral, then your pH will be directly 7. So you need to be a little bit of careful, right? In case of strong acid, strong base mixture. First calculate equivalent of acid base, then do the comparison, and according to that, find the pH. Clear? Now, at least for the strong acid, strong base cases, whether it is a single acid base or whether it is a mixture, you can find the pH easily, right? I hope so. So let's practice some questions, right? From this part, from the calculation of pH of a strong acid, strong base. Can you do that by your own? Following solutions were prepared by mixing different volumes of NaOH and HCl of different concentration. Okay, so 4 cases are given where strong acid HCl is mixed with a strong base NaOH, correct? Now, pH of which one of the following will be equals to 1? So out of these 4 cases, we have to check in which case the pH will be 1. See, here, first thing we need to notice is pH is 1. If pH is 1, that means our final solution is acidic. And our final solution will be acidic only when the equivalent of acid is more than equivalent of base. So of course, it's a case of acid-base mixture. So here you need to get the equivalent first, right? So in all the options, first you calculate the milli equivalent because volume is given in ml. So in the first case for HCl, if I calculate milli equivalent, so n factor of HCl 1, molarity 1 by 10, 1 by 10 into 60 is 6. So this is 6 milli equivalent, right? In second case, NaOH n factor is 1, molarity 1 by 10 into 40. So 40 into 1 by 10, it will be 4 milli equivalent. So point is, in first case, acid is more as compared to base. So there is a possibility that it can give you pH 1. Now calculate equivalent in each case first. In the second case, 1 by 10 molarity into 55 into n factor 1. So it will be 5.5 milli equivalent. And here 45 into 1 by 10 into 1, it will be 4.5 milli equivalent. So in this case also, acid is more. So in this case also, the final solution will be acidic. In the third case, 75 into 1 by 5 into 1. So it is 15 milli equivalent. And here, 25 into 1 by 5 into 1 is 5 milli equivalent. I hope you are getting that to get milli equivalent, I am using that formula, molarity into n factor into volume in ml. So here also acidic solution is possible. In the last case, 100 into 1 by 10 into 1, it is 10 milli equivalent. And 100 into 1 by 10 into 1, it is 10. Now notice, in the fourth case, acid base have equal equivalents. So in this case, final solution, you don't have to calculate. It will be neutral because we have equal equivalents of acid and base. So this solution can't give you pH 1. Now check for the 1, 2, 3. Now for 1, 2, 3, we will have to apply the formula one by one. Let's say in the first case, pH will be minus log. What I said, equivalent of acid minus equivalent of base upon total volume, right? So 6 minus 4 upon total volume 60 plus 40, 100. Now do not calculate, just do it round off. 6 minus 2 is, it's not 6 minus 2, it's 6 minus 4, sorry. 6 minus 4. So it is 6 minus 4, 2 upon 100, so it will be 0.02. And minus log 0.02 can never be 1. Students, you know that minus log 0.1 will be 1, right? So this can't be your answer. Now check the second one. Second case, again pH will be minus log equivalents of acid, milli equivalents of acid 5.5 minus milli equivalents of base 4.5 divided by total volume in ml. So 55 plus 45 will be 100, right? So this will give you 5.5 minus 4.5 is 1. 1 upon 100 is 0.01. And minus log 0.01 will become 2. So even this is your this is not your answer. So of course answer is third one. But let's calculate that also. In third case, pH will be minus log milli equivalents of acid minus base. So 15 minus 5 upon volume in ml, 75 plus 25, 75 plus 25, which is 100. So now here if you notice, 15 minus 5 is 10, 10 by 100 is 0.1 and minus log 0.1 will be equals to 1. So clearly in the third case, your pH is 1, right? So now I think after understanding this question, you have understood that when we mix a strong acid with a strong base, how we can get the pH by comparing equivalents of acid and base first. So here third is the case and third is given in option B. So option B will be the right answer, and this question we got in the NEET 2018, and the same type of question you can expect, right, in the upcoming NEET examinations too. So let's not stop here. Let's do a few more questions from the strong acid, strong base. Can you people do it by your own and give the answer in the chat box? Pause it, solve it, give the answer in the chat box, comment box. I will see your answers personally, and if it is correct, I will give it a like, definitely from my side. So what is the pH of the resulting solution when equal volume of 0.1 molar NaOH and 0.01 molar HCl are mixed? So again we have a case of mixing strong acid, strong base, right? So here NaOH is there and HCl is there. Suppose both are V liter, equal volume. So first if I calculate equivalents of NaOH, so molarity 0.1, volume V, n factor 1. So 0.1 into V, it will come out 0.1 V. And for HCl, if I calculate equivalent, so 0.01 into 1 into V. So it will be 0.01 into V. So these are the equivalents of base and acid. Now if you compare, you will notice that base is more here. 0.1 V is a larger value than 0.01 V. If base is larger, right? That means if equivalents of base is more than equivalents of acid. So for that case, I told you, you can apply this formula. POH equals minus log equivalence of base minus equivalence of acid divided by total volume. Now just do the calculation. Minus log equivalence of base here 0.1 V minus equivalence of acid here 0.01 V. Total volume V plus V. V plus V. V liter this, V liter this. So 2V. Of course, V will be cancelled here, and 0.1 or 0.10 V minus 0.01 V will be 0.09 V. So this is minus log 0.09 V upon 2V. V cancelled, right? This can be written as minus of log and 0.09. I hope you know log m by n can be written as log m minus log n. So 0.0n minus log 2. So now this minus sign is there. So if you multiply with minus, so it will be log 2 minus log 0.09. Now point is the value of log 2 is nearly 0.30 and minus log 0.09 you can calculate it separately, like log 0.09 can be written as log 9 upon 100, right? Again log 9 upon 100 can you can write it as log 9 minus log 100, log 9 minus log 100, and log 9 is log 3 square, so 2 into log 3. Again I am using the log formulas. So 2 into log 3 is 0.48. So 2 into 0.48 is 0.96 minus log 100 is how much? 2. So 0.96 minus 2 will come out minus 1.04. So minus 1.04 we are getting for log 0.09. So if I put it here minus 1.04, right? So nearly this will minus plus, this will come out 1.34, right? I hope you have understood how I got log 0.09. In exams, sometimes they will directly give you the values of 0.09, but sometimes they will just give you the values of log 2, log 3. From log 2, log 3, you can get these values. So log 0.09 is minus of 1.04. So this will be minus plus, finally 1.52. But please remember, this is not pH, this is POH. This is POH, right? From this POH, if you calculate pH, so pH will be 14 minus POH. Okay, one thing, of course, this is how you can do the calculation. It will come out nearly 12 point something. But point is, if you look at the options in this question, we don't even have to do the calculation. Initially only we saw that equivalence of base is more than equivalence of acid, right? So I can say that the solution, the final solution will be basic in nature. And if the final solution is basic, the pH should be greater than 7, right? Only one option is there in which pH is greater than 7, which is 12.65. So I didn't see the option, but in examination, in this type of problem, even without solving, without calculation, you can directly give the answer, 12.65. But of course, if there are other options in which one value is 10, one value is 11, so there you need to do the calculation, right? But I hope this type of problem where you have to solve pH of final mixture of strong acid, strong base, you can solve, you can obtain your answer, right? So in this case, answer will be D, and this question we got in the AIPMT 2015, right? Now, after strong acid, strong base, right? Now let's talk about the weak components one by one, right? Weak cases are also very much important for you. I can say that weak components are more important as compared to strong component. So here also one by one we will talk about. Like first, if you talk about calculation of pH of a weak acid solution. A means there is a one weak acid, its solution is there, and for that you have to find pH. Or there is a one weak base solution, and for that you have to find pH, right? So one by one, let's say first we talk about weak acid. Suppose I have a weak acid like this, HA, whose N factor is 1, monoprotic, right? So this HA will decompose as H plus and A minus. Now here suppose that for your weak acid, the initial concentration is C. So before dissociation, ions will be 0. Now here, because it is weak acid, it is weak electrolyte, it will not dissociate 100%. So in this case, to get the concentration of ions, I will require degree of dissociation. So for this weak acid, if your degree of dissociation is alpha, you know what is next to do. What is the next thing we have to do? If degree of dissociation is alpha, then the dissociated amount will be C alpha, right? So after dissociation, acid will remain how much? C minus C alpha, H plus will be C alpha and anion will be C alpha. And now you have got the concentration of H plus. For this weak acid solution, you can say that concentration of H plus ion is nothing but C alpha. And once you have got the H plus concentration, you know how to get pH. Here concentration of H plus is C alpha, right? And of course we can find pH, but point is sometimes they will manipulate this expression, right? Like instead of C alpha, I can write it as C into K upon C. Basically, from this I will get concentration in terms of dissociation constant. If I take C inside the square root, so it will be under root of C square into K by C. 1 C will be cancelled, so square root of K into C. So H plus concentration can be either written as C alpha or under root of K into C. And from here, if you calculate the pH, students, it will be minus log concentration of H plus, which is under root K into C, and it can be written as K into C power half, because square root is nothing but power half. Half will be outside, so it will be minus of 1 by 2. And log K into C can be expressed as log Ka plus log C. Now please remember, I told about the pK terms. Remember, I have a minus sign here. If I multiply with minus in this expression, so half into this will be minus log K and this will be minus log C. Minus log K can be also written as pKa, right? So the formula of pH for weak acid can be written as half minus log K will become pKa, and this will remain as it is, minus log C. So many points are there, right? So many possibilities are there. In your question, if only C alpha is given, so you can directly get H plus. From C alpha, you can find pH. If they have given pK in the question, then you can apply directly this formula, half pK minus log C. If they have given the dissociation constant value, so then you can apply this formula, right? Under root of K into C, you can apply. From this you can get H plus, and then you can find pH. So that's how you can obtain the pH of a weak acid solution. And in the same way, you can also obtain the pH of weak base solution, right? Suppose I have a weak base like this, and factor 1, it will decompose like this. Now I'm not going to write the same thing, right? C 0 0, C minus C alpha, C alpha. Here I can directly say that in the same way, right? Like in the previous case, you were getting the concentration of H plus ion for weak acid as C alpha. So in the same way, in case of weak base, what you get concentration of OH minus as C alpha. This can be also written as under root of Kb into C. And finally, in this case, directly you won't get pH. You will be getting what? POH. And the formula of POH here, it will be pKb minus log C. So isn't it the formulas are quite same? Like in weak base, we are getting half pKb minus log C, right? In weak acid, we are getting half pK minus log C. The only difference is in case of weak acid, we are getting this as pH. pH is half pK minus log C. And for weak base, the half pKb minus log C term is nothing but your POH, right? So from these formulas, you can find the pH of weak acid, weak base. And suppose, try to remember this, but suppose if you forget this, so anytime you can derive within 10-20 seconds. It will take a little bit of more time, but you can derive this formula very easily. And you can find the pH of weak acid and weak base. Now, from this weak acid, weak base pH calculation part, right? Let's practice some question. And I will be much more happier if you do this question before me. Pause it. Try to do it by your own first. right? Then see my solution. 0.01 molar acetic acid, weak acid solution is there, which is 1% ionized. So they have given the percentage dissociation, percentage ionization. Means alpha into 100, which we say percentage dissociation is 1. So alpha will be how much? 1 upon 100 means 0.01. So degree of dissociation indirectly they have given as 0.01. Concentration of weak acid is given 0.01 molar. Now, then pH of this acetic acid solution. pH of this acetic acid solution. So in this question, they have not given the pKa value or Ka value. They have given what? Alpha and C. So in this case, what we can use? We can directly use this term, that concentration of H plus is C alpha. Here C is nothing but 0.01 molar and alpha is how much? 0.01. So 0.01 into 0.01 is 10 power minus 2 into 10 power minus 2 is 10 power minus 4, right? And if I have got the concentration of H plus, I can directly find pH as a minus log H plus. So minus log concentration is 10 power minus 4. You know that minus 4 will be outside. So minus of minus 4 into log 10 and it will be 4. So here pH of this weak acid solution is directly 4. Right? In similar type of question, suppose instead of alpha, if they give you Ka, right, or pK, so you can apply that formula, half pKa minus log C. For weak base, POH equals to half pKb minus log C, right? So in this case, the correct answer is 4 and option should be D. So of course that's your answer, and this question is very much recent. We got this direct question of pH of weak acid in the NEET 2022 examination. So now students, after pH of weak acid and weak base, right? Now it's time to talk about how do we calculate the pH of salt. But of course, in terms of salt, in case of salt, the mainly you get questions from the pH calculation. But of course, before we discuss about the formulas of pH of salt, first we have to understand what is the meaning of salt hydrolysis, right? I hope you know salt, right? Salt is formed due to the reaction between acid and base, right? And in this chapter, even the salt is categorized into different parts according to the strength of acid and base, right? You can have a salt of weak acid, strong base. You can have a salt of strong acid, then weak base. You can have a salt of weak acid, weak base. And you can also have a salt of strong acid, strong base, correct? For example, if you talk about sodium acetate, CS3COONA. So sodium acetate is created due to the reaction between CS3COOH and NaOH. So weak acid, strong base is reacting to give you this. So this is called salt of strong acid, weak acid, strong base. Similarly, if you talk about salts like NH4Cl, right? Ammonium chloride. So it is created by the reaction of ammonium hydroxide and HCl. Ammonium hydroxide is weak base, HCl is a strong acid. Similarly, if you talk about ammonium cyanide or ammonium acetate, right? So ammonium cyanide is created by ammonium hydroxide and HCl. Both are weak base, weak acid. And if you talk about strong acid, strong base, so salts like NaCl, KCl, KBr, right? They are the salts of strong acid, strong base. Point is, when we dissolve any of these salts into water, right, we observe salt hydrolysis. In salt hydrolysis, basically what happens, either the cation or anion part of salt will associate, will combine with water molecule to produce, right, certain amount of H plus or OH minus ion, right? And that phenomena is called as salt hydrolysis. Like for example, if you talk about a salt of weak acid, strong base, right? So by default, all these salts are strong electrolyte, like CS3CONA. So CS3CONA, this is a salt. So this salt is strong electrolyte. So when you dissolve this in water, it will completely ionize into CS3COO minus, right, and Na plus. But out of CS3COO minus and Na plus, the anionic part here, that is CS3CO minus, it will combine with water molecule to produce some of acetic acid along with some of the OH minus ion, right? So I can say that in case of weak acid strong base salt, the anionic part of salt will combine with water to give you this molecule and OH minus. Now this process is called salt hydrolysis. Similarly, if you talk about salt of a strong acid and weak base, so in this case, the cationic part will go through hydrolysis, right? Like if I take ammonium chloride. So ammonium chloride, it's a strong electrolyte. So first ammonium chloride, it will decompose into water as NH4 plus and Cl minus. Later on, the cationic part of this salt, that means NH4 plus, will combine with water to produce again some of the NH4OH and some of the H plus. So I can say that in case of a strong acid weak base salt, right, the cation will go through hydrolysis, right? And when you talk about weak acid weak base, so in this case, both cation and ion will go through hydrolysis, right? Like if I take NH4CN, so in case of NH4CN, right, I will have NH4 plus ion, I will have CN minus ion, and when they will combine with water, right? So NH4 plus will combine with water to give you NH4OH, and the Cn minus part will combine with water to give you HCl. So point is, when we have salt of weak acid strong base, in that case we have anionic hydrolysis. In case of strong acid weak base, we have cationic hydrolysis. And in case of weak acid weak base, we have both cationic and anionic hydrolysis. But when it comes to salt of strong acid strong base, right? So in this case, there will be no hydrolysis. There will be no hydrolysis. Why? Now let me tell you that point. Because see, when you dissolve NaCl in water, right? So NaCl in water, it will decompose into Na plus and Cl minus. Now in this NaCl, if you notice, if Na plus combines with water, so it can produce NaOH, which is a strong electrolyte. And if Cl minus combines with water, it gives you HCl, which is nothing but strong electrolyte. Now at the beginning, if you remember, when I talked about electrolyte, so there I mentioned a point. Remember that when you have a solution of a strong electrolyte, so there should not be any molecule present, right? The solution of a strong electrolyte has only ions in it. So if Na plus or Cl minus, after combining with water, after combination with water, it is giving you strong electrolytes like NaOH or HCl. So NaOH, HCl molecules can't be formed. So that means what? In these cases, Na plus Cl minus cannot combine with water, right? Because you can't have NaOH or HCl molecule in your solution because they are strong electrolyte. And same reason you can give here, like in case of weak acid strong base, why we are having only anionic hydrolysis? Why the cationic part is not getting hydrolyzed here? Because like suppose if I take sodium acetate, so acetate combines with water to give you weak electrolyte, right? And weak electrolyte can have both ions and molecules in the solution. But from the same sodium acetate, if I combine Na plus with water, what I get? I get NaOH along with H plus, right? NaOH can't be present in a molecular form. So that's why the hydrolysis of Na plus is not possible. Only hydrolysis of that cation anion will be possible here, which can produce a weak electrolyte like acetic acid, NH4OH, HCl. So please remember, that's what is salt hydrolysis. Salt hydrolysis means combination of either cationic or anionic part of the salt with water, right? And cation or anion, they will combine with water to produce either weak acid or weak base along with H plus or OH minus, right? And in case of weak acid, weak base, you will have hydrolysis of both cation and anion part. If I have a salt of strong acid, strong base, so there will be no hydrolysis. Now point is, when it comes to calculation of pH of these types of salt, so for these types of salt, pH is calculated with help of this salt hydrolysis. And that's why we talk about salt hydrolysis here. Like if I give you example of the first one, right? Suppose I have a salt of weak acid strong base. I have a salt of weak acid strong base, right? So for example, again I am taking, let's take a different one. Let's take NaCN. NaCN is made up of NaOH, strong base, and HCN, weak acid, right? So in NaCN, again, Na plus will not have hydrolysis, but cyanide part will have hydrolysis. So this cyanide part, when it will combine with water, it will give you what? It will give you HCN along with OH minus. Now, in order to get the pH value, right, you need to calculate the hydrolysis constant here. Like in case of electrolytes, we used to say dissociation constant, ionization constant. But in case of salt hydrolysis, we call it hydrolysis constant. So if I try to calculate hydrolysis constant here, like assume that initially the NaCN concentration was C. So from C concentration of NaCl, I will get C concentration of cyanide. Before hydrolysis, this will be 0, right? Suppose if degree of hydrolysis, just like degree of dissociation, we have a term here called degree of hydrolysis, H. If degree of hydrolysis of this salt is H, right, then the hydrolyzed amount will be C into H, CH. And after hydrolysis, the anionic part will remain C minus CH. And these products will be how much? CH and CH. Right? From here you can notice that we are getting the concentration of OH minus as CH, and from here you can proceed with the calculation of POH, right? You can say that POH will be nothing but minus log C of H. Now here you can replace this degree of hydrolysis in terms of hydrolysis constant, right? Simply if I calculate hydrolysis constant from this in terms of CH, right? So concentration of HCN power 1, OH minus power 1, concentration of CN minus power 1, this will give you CH power 1, CH power 1 upon C into 1 minus H. Again, similar concept that we used in the Ostwald dilution law. If H is smaller than 1, then 1 minus H will be 1. 1 C will be cancelled from this. So from here, H will be equals to under root of KH by C. So I can substitute that here. Now I can say that POH will be how much? Minus log of C times under root of KH by C. Or it can also be written as minus log of under root of KH into C. Correct? Not only that, this KH can be written in terms of KW and Ka. Right? Like for this reaction, the constant you get is called KH, this hydrolysis constant. In this case, you have the HCN, weak acid. So for HCN separately, you can write the expression of Ka, right? Ka of HCN will be concentration of H plus into Cn minus upon concentration of HCN. If you multiply the hydrolysis constant of salt with dissociation constant of weak acid, it will be equals to Kw, right? You can multiply that, just the expression part. The expression of KH, the expression of Ka, just you multiply, you will get concentration of H plus into concentration of OH minus, which is nothing but Kw. So from here, this KH can be further written as Kw by K. And if I substitute KH here in terms of Kw by K, then I can obtain my POH in terms of Kw Ka or later on PKW Pka. So that's how you obtain the formula. You can substitute this, you can derive the formula. But the point is, I will suggest that at least for the salt clays, please memorize the formula, because it will save a lot of time for you. Because in your examination, if you try to derive this, it will take huge amount of time. So for salts, right, especially the pH of salt, please memorize the formula with some trick, right? I have a trick for you. Please listen. If you have a salt of weak acid strong base, if you have a salt of strong acid weak base, and if you have a salt of weak acid weak base, we are not writing strong acid strong base because for that salt pH will be always 7. So for these three cases, write down like this: pH, pH, pH equals half, 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 square bracket, 14, 14, 14. So this much is common in all the formula of any kind of salt, right? So I memorize like this: pH equals to half, 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 14, 14, 14. Now the main point, now the logical point. If you notice, in the first salt, the acid is weak. And if you observe, right, these terms like alpha, K, Pk, they are valid only for weak electrolyte, right? If you consider a strong electrolyte, so for a strong electrolyte, alpha is 1 and K is almost infinity, Pk is undefined. So these terms are applicable only for the weak electrolyte. So in the formula, only the terms of weak component will be there. Like in the first salt, base is strong, so you will not have Kb or pKb in the formula. Acid is weak, so you will have terms of acid, right? For acid we have pKa, and for acid please remember plus, acid plus. So here the formula will be half 14 plus pKa for that weak acid, again plus log C. C is the concentration of the salt. Similarly, in the second case, if you notice, acid is strong, so you won't have any term of acid here. But base is weak, so you will have terms of base. And for base, minus, acid plus base minus, acid plus base minus. So for weak base, I will write minus pKb of the weak base minus log C, right? And in the last case, when both are weak, you will have terms of both acid and base. But again, acid plus base minus, right? So plus pKa minus pKb, and you won't find log C in this because we don't get log C in the formula of pH of salt of weak acid, weak base. So this formula, if you remember, you can directly solve questions of salt of pH, right? And if you want to talk about the derivation, then I just gave a hint how to derive. In the same way you can calculate for strong acid, weak base, or weak acid, weak base, same way. Correct? But apart from pH, what I want, please remember few more points. Like you saw one thing, that in case of weak acid, strong base salt, when we talk about hydrolysis, so there we have this relation, hydrolysis constant into Ka of weak acid is equals to Kw. So similarly, when you have a salt of strong acid, weak base, so in this case what you get, hydrolysis constant into Kb of that weak base is equals to Kw. And similarly, for weak acid, weak base, you get hydrolysis constant into Ka into Kb equals to Kw, right? One more point. In case of weak acid, strong base, you get degree of hydrolysis equals to under root of Ka by C. You saw that, right? You saw that here, right? H will be under root of, not K, sorry, Kh by C. Of course, it's a hydrolysis constant. So Kh by C. Similarly, in case of strong acid, weak base, you will be getting degree of hydrolysis as under root of Kh by C. But in case of weak acid, weak base, right, the hydrolysis, degree of hydrolysis will come out simply under root of Kh. So here you won't have the concentration term. And because here degree of hydrolysis is under root of Kh, that's why in the final pH formula you don't have the log C term here. So relations between the dissociation constants of hydrolysis constant and Kb with Kw, the expression of degree of hydrolysis, and finally, of course, the most important point, pH. Right? So these pH formulas you need to remember always in your mind. And also, what is the meaning of salt hydrolysis, you should know. If this much you know, you can solve all the NEET problems, believe me, right? So let's do some questions, right? Let's do some questions, correct? We talked about what is salt hydrolysis, and we also saw what is the formulas for pH, right? I wrote down the formula, and please try to memorize that by acid plus, base minus. When you have weak acid, so only weak acid term will be there. When you have weak base, only weak base term will be there, pKb, pK, right? When both are weak, then both pK, pKb will be there in the formula. So let's do some questions from this. Can you do it before me? Pause the video. Try to do it by your own first, everyone. The pKb of dimethylamine, weak base, and pKa of acetic acid, weak acid, are 3.27, 4.77 respectively at T Kelvin. The correct option for the pH of dimethyl ammonium acetate. So dimethyl ammonium acetate is your salt here. And clearly it's a salt of weak base and weak acid. It's a salt of weak base and weak acid. And we have to calculate the pH. Directly apply the formula. For weak base, weak acid, formula is pH equals to half square bracket 14 plus pKa minus pKb, right? So half 14, what's the value of pKa? pKa is the second one, 4.77. So 4.77 minus what's the value of pKb? pKb is the first value, which is 3.27. 3.27. I hope you can calculate this easily, right? Half 14, 4.77 minus 3.27 will be 1.50. 14 plus 1.50 is 15.5. So half into 15.5. And half into 15.5 will be like 2 sevens are 7.75. So 7.75 if you check the options. So we have the option D here. So clearly option D is there. That will be the right answer. So this was the case of weak acid, weak base. In the same way, you can have question from weak acid, strong base, right? You can have question from strong acid, weak base. But every time you have to use the formula when you calculate pH of salts. Definitely here answer is D. And this question we got in the NEET 2021 examination. Correct, students? So now, can you answer this question? It's not a calculation problem, it's a logical problem from the salt solution. Question is, which of the following salt will give highest pH? Now, highest pH means what? Highest pH means when your solution is basic, right? We can directly answer this. Students, please focus here. If you have a solution of weak acid, strong base, weak acid, strong base. So if it is made up of a strong base, then this type of salt will be automatically basic in nature. If you have a salt like this, a strong acid, weak base, right? So this type of salt will be 100% acidic in nature because it is made up of a strong acid. When you have a weak acid, weak base salt, so in that case you cannot say with certainty because it will depend on the ionization constants of your acid and base, the pK, pKb values. But at least for these two cases, you can say that salt of weak acid, strong base will be basic and salt of strong acid, weak base will be acidic. Highest pH means basic, and basic means we have to discover which salt is made up of weak acid, strong base. Now one by one. KCl, it is made up of KOH, HCl. So it's a salt of a strong acid, strong base. Its pH will be 7. NaCl, again NaCl is made up of NaOH and HCl. So it is again salt of strong acid, strong base. So its pH will be also 7. Sodium carbonate, it is made up of NaOH, strong base, and H2CO3, weak acid. I think that's our answer, right? Na2CO3 is a salt of weak acid, strong base. Weak acid, strong base salts are basic in nature, right? And if you talk about copper sulfate, so it is made up of CuOH whole twice. D block metal hydroxides are generally weak bases. Along with H2SO4, H2SO4 is a strong acid, right? So this salt will be acidic in nature. This salt, D, will have the lowest pH value, and C will be basic in nature. It will have the highest pH value, and A and B have neutral pH value, pH 7. And they are asking for highest pH, so definitely in this case answer will be C. That means salt of weak acid, strong base. And yes, that's your answer. And this question we got in the AIPMT 2014 examination, correct? But this is about what is the nature of the salt, whether it is acidic or basic or neutral. And that we can just decide by looking at the formula, because from formula we can obtain that any particular salt, it is made up from which acid and which base. Clear? Now, after salt, after pH of salt, right, we have a very interesting topic here, common ion effect, but it is again somewhere related with your degree of dissociation. So we talked about degree of dissociation, especially that Ostwald dilution law, remember? In the Ostwald dilution law, I told you that degree of dissociation will be suppressed when you increase the concentration, right? Common ion effect is also related with degree of dissociation. Point is very simple. If you have a weak electrolyte, right? And in the solution of weak electrolyte, if you add some common ion, of course, common ion will be added with help of strong electrolyte, right? So in the solution of weak electrolyte, if you add a common ion, right, by adding a strong electrolyte. Point is very simple here, right? Like if I take any weak electrolyte, let's say I have taken again the most common one, acetic acid, right? So if I take a pure solution of acetic acid, like acetic acid plus water, right? Now no other acid or base is there. And in that case, of course, it will ionize. Suppose that in the pure state, it is ionizing, and here its degree of dissociation is alpha 1, right? Now, the same acetic acid with the same concentration of acetic acid, if I add with another electrolyte, I add the same concentration of acetic acid. If here the concentration is C and here also the concentration is C, same concentration of acetic acid. If I add with strong electrolytes like HCl, H2SO4, HNO3. So point is, HCl will give you H plus ion, and acetic acid also gives H plus ion, right? So here H plus ion will be common. So point is this, when I will add HCl in the solution of acetic acid, so due to presence of common ion, that is H plus ion, the degree of dissociation of this acid will suppressed, right? Now here, if I calculate degree of dissociation and it is coming what? Alpha 2. So clearly alpha 1 will be higher than alpha 2. So in the pure state, acetic acid will have more dissociation as compared to when acetic acid is present with HCl or is present with common ion, that is HCl, that is H plus. And if you try to define the common ion effect, the definition is in the same way, like when a strong electrolyte is added into the solution of weak electrolyte having some common ion, right, then the degree of dissociation or degree of ionization of weak electrolyte is further suppressed, right? So alpha will be suppressed due to presence of common ion. That's the point. Now, sometimes you get questions with help of common ion effect, right? Sometimes you will be getting direct question from common ion effect, like they will give you a weak electrolyte, it will be present with some strong electrolyte, right? And there you will have to find the alpha with help of K. So they will give you the dissociation constant. The dissociation constants will be given to you, right? And from this dissociation constant, you will have to obtain what? Alpha. Now let me tell you with an example how you can solve these types of questions, right? Like suppose I have a weak acid HCl, right? And I have a solution for this in which the concentration of HCl is 0.01 molar. So clearly it will ionize into H plus and Cn minus. Initially before dissociation, the concentration of ions will be 0, and here for HCl, if degree of dissociation assumed to be alpha. Then after dissociation, it will be 0.01 minus 0.01 alpha, and the ions will be 0.01 alpha and 0.01 alpha. I don't have to tell you that 0.01 alpha part of HCl will give you 0.01 alpha part of H plus and 0.01 alpha part of Cn minus. Now suppose in the same solution you have added HCl. How much? 0.1 molar. So HCl, which is a strong acid, strong electrolyte, HCl will decompose into H plus and Cl minus, and 0.1 molar part of HCl will give you 0.1 molar part of H plus and 0.1 molar part of Cl minus. Now if these two are present in the same solution, then H plus is the common ion here, because H plus we are getting from HCl also and H plus we are getting from HCl also. Now suppose here if I calculate the dissociation constant Ka of this HCl, so it will be concentration of H plus ion power 1 into concentration of cyanide power 1 divided by concentration of HCl power 1, right? Now in your questions the value of K will be given to you. K will be known to you. Now concentration of H plus, which is a common ion, please remember that in any calculation we always take total concentration of the common ion. Total concentration, although you are doing calculation of K for your weak acid part. But because in the calculation of K, I need the concentration of H plus, which is common ion, so I will be taking the total concentration of H plus. Now here the total concentration of H plus is 0.01 alpha from HCl and 0.1 molar from HCl. So total concentration of H plus I can write as 0.01 alpha plus 0.1. That's the concentration of H plus. And then concentration of Cn minus is simply 0.01 alpha divided by concentration of HCl will be 0.01 into 1 minus alpha. Now, when you will be doing numericals from this, please remember what will happen. Your alpha will be very small. If your alpha will be very small, then this term will be neglected as compared to 0.1. So in the numerator, you have only one alpha term, 0.01 alpha. Also, alpha is smaller as compared to 1. So 1 minus alpha will become 1. So due to common ion, the calculation part will become very easy to you, right? And if I know the Ka value, I can find alpha from this. And please always remember this point that whenever we get this type of summation of something into alpha, so here alpha will be ignored. This term can be written as 0.1 into 0.01 alpha divided by 0.01, right? And same type of concept of common ion effect you will also get in the solubility product part. When you talk about solubility product, so there also you get the same point, right? Here we calculate alpha from dissociation constant, and in the solubility product part, you will be calculating solubility from KSP using the common ion effect in the similar manner, right? So now I think you have understood common ion effect, and in the calculation part, we have to always assume the total concentration of common ion, right? So with this, now let's move into the next pH calculation, or you can say buffer solution or pH calculation of the buffer solution, right? So first point is, what is the meaning of buffer solution? I hope you people know the meaning of buffer solution, right? Generally in a solution, when we add acid base, so that changes the pH value. But if it is a buffer solution, so when I add small amount of acid, please remember small amount of acid or base into it, or if I do dilution, so with that the pH will not change. So buffer solution is a solution which resists change in pH when small, or I should say very small, when very small amount of acid, base or water is added into it, right? Now obviously buffer solution is not a simple solution, right? There are certain conditions to prepare buffer solution. Like the first condition is you should have some weak electrolyte. By using only strong electrolyte, you can't prepare a buffer solution. To prepare a buffer solution, you need a weak electrolyte like weak acid or weak base, right? And with that, if you mix its corresponding conjugate acid base, remember Bronsted-Lowry concept? So if I take a weak acid, and with weak acid, if I add its conjugate base, or to get conjugate base, we can add certain salt here. So weak acid plus its conjugate base or weak acid plus its salt, right, can create a buffer. And when you create buffer from weak acid, so that is basically called as acidic buffer. This is called acidic buffer. Similarly, if you take weak base, and with weak base you take its corresponding conjugate acid or its salt, right? So that buffer which is created by weak base and its salt is nothing but a basic buffer, right? And these acidic and basic buffer, right, they resist change in pH due to common ion effect, So you can say that buffer solution is a kind of application of your common ion effect. And sometimes you will be getting direct question from this, right, of identification, like whether a mixture is acting as acidic buffer or whether a mixture is acting as a basic buffer, right? Now, the main thing is in buffer solution also, we need to do the calculation of pH. And just like salt, for buffer solution also, your formula is very important. And for both acidic basic buffer, we have kind of similar formula, so it can be easily memorized, right? Like when you have acidic buffer, right? So in case of acidic buffer, you can write like this: pKa plus log concentration of conjugate base divided by concentration of weak acid. So in case of acidic buffer, pKa plus log conjugate base concentration upon weak acid concentration this gives you the pH of the buffer solution. And similarly, if you have a basic buffer, so in that case, pKb, please observe it's similar. There pK, here pKb, plus log, there we have conjugate base, so here we have conjugate acid. There we have acid, so here we have weak base. So with the similar formula, in case of basic buffer, you will be getting POH instead of pH, right? So please note down, because again from the buffer solution part, at least see, we have different pH calculation, but from the salt and buffer part, you will be getting pH calculation direct from the formula. So for salt and buffer, right, if you remember the formulas of pH, the work will be very easy for you, right? So that's the formula of acidic buffer, that's the formula of basic buffer, correct? One more term is there, which is generally not asked in the NEET examination. It is called buffer capacity. Buffer capacity. Actually, when you add small amount of acid base, so then buffer resists change in pH. But point is, when you add much more amount or extra amount or excess amount of acid base, so in that case, even for buffer also you will have change in pH, right? So how much change in pH you have upon how much acid or base you have added, right? So that kind of comparison is called as buffer capacity, right? Change in pH with respect to how much amount of acid or base you have added, how much amount of acid or base you have added. So that comparison is called as buffer capacity. But in NEET exam, we never get question from buffer capacity. We get either from the identification of buffer, whether it is acidic or basic, right? Or we get directly questions from the pH, right? So now I think it's time to solve some questions from the buffer solution and its pH calculation. Please pause the video, try to do it by your own first, then match the answer with me, right? But I will have to solve, I can't stop. But you can stop the video anytime. Question is, the pH of the solution containing 50 ml each of 0.1 molar sodium acetate and 0.01 molar acetic acid is. So first thing is, in this question they have not mentioned whether it is buffer, whether it is strong acid, weak base. You will have to identify by your own that if they are saying that we have a mixture of sodium acetate, and along with that we have acetic acid. So you need to identify here that if I am mixing a weak acid with its corresponding salt, so it is nothing but weak acid plus salt gives you acidic buffer. So this mixture will function like a acidic buffer, right? And if it is acidic buffer, so to calculate pH, we can directly apply this formula, right? pH equals pKa plus log concentration of conjugate base divided by concentration of weak acid, right? So here pK is given 4.57 plus log concentration of conjugate base you can obtain from the salt, right? If your sodium acetate is 0.1 molar, then automatically the acetate ion you will be getting will be also 0.1 molar. So 0.1 divided by weak acid concentration is given 0.01. Now if you notice, 0.1 by 0.01 will come out 10. Right? And log 10 is 1. So 4.57 plus 1 will come out 5.57. So can you see this? A direct formula based question. The answer will be of course A here, 5.57, and of course A. And this question we got very recently in the NEET 2022 examination, right? So for acidic and basic buffer, for both case you need to remember the formula, correct? Now, can you do this question? A logical one, but of course, if you have understanding of buffer solution, you can solve it. Question is, an acidic buffer is prepared by, how we prepare acidic buffer? So weak acid plus its conjugate base or salt, right? Weak acid, its salt, right? Or from salt you can get what? Conjugate base. So of course here the answer will be A, right? Weak acid plus its conjugate base gives you the acidic buffer, and a weak base plus its conjugate acid gives you the basic buffer. And this question again we got very recently in the NEET 2023 examination. Just from the logic, just from the understanding of what is acidic buffer, what is basic buffer, and how do we prepare acidic and basic buffer, right? Let's move ahead. Let's move ahead. Can you do this question, all of you? Which composition will make the basic buffer? So in this case, in different options, you are given with mixture, but you will have to identify that which will act as basic buffer. So for basic buffer, we should have what? We should have weak base. Along with that, we should have the salt of weak base with strong acid. So in the first option, they are mixing HCl, which is a strong acid, with NaOH, which is a strong base. Now here you notice, you do not have any weak base component. If you don't have weak base, you can't prepare basic buffer from this. In second case, you have a strong base, and here you have a weak acid. So although acidic buffer is possible from this because weak acid is there, but still if you notice, because these two will neutralize, you will have a reaction between NaOH and acetic acid, and the equivalence of milliequivalence of NaOH is 15 to 0.1 means 5, and milliequivalence of acetic acid is 0.1 into 25, 2.5. So here the final solution, you will have base only. You won't left with any kind of weak acid. So this will not at all form any buffer, right? For buffer, the acid should be in excess. And in this case, if you take excess amount of CH3COOH, so that will give you acidic buffer, not basic buffer. In the third case again, you have acetic acid with NaOH, so that may create acidic buffer depending upon amount. But again here you have 0.1 molar 100 ml means 10 milliequivalents of acid, and 100 into 0.1, 10 milliequivalents of base. So perfect neutralization will happen. You are not left with any amount of acid. So even this can't create a buffer. So ABC will not at all form any kind of buffer, neither acidic nor basic. In option D, if you notice, you have HCl, strong acid, you have NH4OH. So here you have a weak base, right? And if you check, because only the presence of weak base is not enough, it should be in excess, because when your weak base will be in excess, after reaction, some base will be left, some salt will be formed, so then it will create a buffer. So you need to check the amount also, right? 200 ml into 0.1, so it is almost 20 milliequivalents, right? And 0.1 into 100 into 1, this is 10 milliequivalents. So here clearly the weak base is in more amount. So after reaction, HCl will be completely consumed. Some NH4Cl will be formed, your salt, and some NH4OH will be left. So finally, you will have a mixture of weak base and its salt. So that will function as basic buffer. So in this question, of course, the answer should be D, and yes, it is your answer. And this question we got in the NEET 2019 examination, right? So now students, we are done with all the pH calculation. I hope you have understood that in pH part we have buffer, we have salt, we have a weak acid, weak base, mixture of strong acid, strong base, right? Then single strong acid, single strong base. But for all those cases now, you can find the pH. Can you answer this one, all of you? Another question just from the identification of buffer. Which one of the following pair is not an acidic buffer? Is not an acidic buffer, means in which case we do not have a weak acid with its salt. So first one is HClO4. HClO4 is a strong acid. This is the salt. Here the first one is the answer, right? Because for acidic buffer we need weak acid. Here we have a strong acid. So first one is not acidic buffer, so A will be answer. And if you check the rest of the options, so acetic acid is weak acid plus salt, acidic buffer. H2CO3 is a weak acid plus its salt, acidic buffer. S3PO4 with Na3PO4 can function as a acidic buffer, right? But in the first case, because HClO4 is a strong acid and strong acid cannot form a buffer or acidic buffer, so A will be your answer. right? So this question was basically based on the condition that how we create a acidic buffer or basic buffer using weak acid salt and weak base plus its salt. And this question we got in the AIPMT 2015 examination, right? Now, moving ahead, can you do it by your own, all of you? One more question from the buffer itself, but again, it will be a direct question for you. You have to just apply the formula of pH of buffer solution. Question is, the dissociation constant of weak acid is 10 power minus 4. So they have given Ka. Ka is 10 power minus 4. Now anytime from Ka we can find Pk, because we know that Pk is minus log of K, right? So minus log of 10 power minus 4. Minus 4 will be outside. Minus 4 minus plus 4 log 10 1. So here Pk is 4. Now in order to prepare buffer solution with pH 5, of course, because it's a weak acid, so we are going to prepare acidic buffer here, and we have to find the ratio of concentration of salt and acid. So what we can do, we can directly apply the formula. pH is pKa plus log concentration of salt. Instead of salt, it's better always to write conjugate base upon concentration of acid, right? So this term we have to find. Now, they have given the pH, no? pH is 5. Pk is given 4 plus log concentration of salt or conjugate base divided by concentration of acid. Now here, 5 minus 4 is 1. So log this is 1. So anything inside log, if it is 1, so this term will be how much? 10. So concentration of salt upon acid is 10. Or 10 upon 1. So clearly your answer will be B here, right? So whatever question we are getting from a buffer, it is directly based on the formula of pH of buffer. And here of course answer is B, and this question again we got in the NEET 2013 examination, right? So now I think buffer, salt, acid, base, strong base, weak acid, weak base, every kind of pH calculation you can do. But of course, you know very well that after this session, you have to practice more and more questions, right? And for that, we are providing the DPP where? In the video description, right? And also those DPPs you can get at what? PW app, right? So download app, and there you can get DPPs of not only this chapter, you can get the DPPs of the rest of the chapters as well as for the rest of the subjects, right? So get help from the PW app, all of you. Now we are into the final topic of this chapter, which is ionic product. And ionic product and one more point, solubility product, we should always discuss together because both are similar terms. Both are similar terms. The only difference is solubility product is calculated only when your solution is saturated, while ionic product can be calculated at any instance, right? So ionic product means what? Ionic product is a very simple thing, right? It is nothing but multiplication of concentration of ions in a solution for an electrolyte. Right? Like suppose if I prepare a solution of AgCl, I have prepared a solution of AgCl. So in the solution, right, AgCl is sparingly soluble, right, very less soluble. But whatever part of AgCl is soluble, that part will give you what? Ag plus ion and Cl minus ion, right? And if you write that in equation form, so AgCl will decompose into Ag plus and Cl minus. Now, at any time, if I know what is the concentration of Ag plus and Cl minus I have in the solution, right? So from that I can find my ionic product. So for here, for AgCl, the KIP, the ionic product of AgCl is nothing but concentration of Ag plus power coefficient, which is 1, into concentration of Cl minus power coefficient 1. That's it. For any electrolyte, for any sparingly soluble salt, right, the concentration of its ion to the power stoichiometric coefficient if you multiply, so that gives you the ionic product, right? Now at any time for any salt, if I know the concentration of ions, I can find my ionic product, and that's a very easy task. Like for example, suppose I have this salt Na2SO4. I have this salt, okay, Na2SO4. Now, someone is saying that I have prepared a solution of Na2SO4 in which the concentration of Na plus ion is 0.1 and the concentration of sulfate ion is 0.2. Now, point is, if I know the concentration of ions, I can easily find KIP. I can easily find ionic product. Basically, Na2SO4 in your solution, it will decompose as twice of Na plus sulfate, right? So first always write the expression. Here the ionic product of sodium sulfate will be concentration of Na plus ion power 2 into concentration of sulfate ion power 1 coefficient, right? So here ionic product of Na2SO4 is concentration of Na plus power 2 concentration of sulfate power 1. But in this case, they are saying that I have the known concentration of these two. So I can substitute that. If concentration of Na plus is 0.1, I can write it 0.1 here. So 0.1 power 2. If concentration of sulfate is 0.2, I can write it here 0.2. So you understood, right? If I know the concentration of ions of an electrolyte, anytime I can find KIP, anytime I can find ionic product. And in this case, the ionic product will be 0.1 square is 10 power minus 2. And 0.2 is written as 2 into 10 power minus 1. So finally it will be 2 into 10 power minus 3. Clear? So you understood the meaning of ionic product for any salt, for any electrolyte, right? Multiplication of concentration of its ion raised to the power coefficient gives you KIP, ionic product. Now we have a similar term here which is called as solubility product. Solubility product is also calculated in the same way. You have a salt, you have your salt, right? So multiplication of concentration of its ion raised to the power stoichiometric coefficient. But solubility product is calculated only when your solution is saturated. See, when I talked about ionic product, right, I didn't said that whether it is saturated, unsaturated, supersaturated, because it doesn't matter. KIP can be calculated for any case. But when I am saying solubility product, so for solubility product, the first point is it is calculated for saturated solution. I hope you know very well about unsaturated, saturated and supersaturated solution. Unsaturated solution is the one in which more solute can be added, right? Saturated solution is the one in which more solute cannot be added, and supersaturated is the one in which excess amount of solute has been added because of high temperature. So there is a chance of precipitation in that. There is a chance of precipitation in that, right? But when your solution is saturated, so for saturated solution, when you calculate ionic product, so that ionic product is called as KSP. I can write it like this. The KIP of saturated solution is nothing but equals to KSP. Right? One more point. When we calculate KSP, so we define a term called as solubility. And solubility in this chapter is denoted by capital S. Now, what is solubility? Solubility of any salt is the maximum amount, right? The maximum moles of salt that can be dissolved per liter of solution. For any electrolyte, the maximum amount that you can dissolve in per liter solution, right? So that is called solubility. And point is, in any solution, when maximum amount of salt is present, so automatically that solution is saturated now, right? So whenever you have a saturated solution, so for saturated solution, the molarity of solution will be equals to the solubility of solution. The molarity of solution will be equals to the solubility of solution, right? But always remember that KSP is calculated when your salt solution or electrolyte solution is saturated. Now point is, if I take a random example, let's take AlCl3. And let's say for AlCl3, I have to find the KSP. So point is, for AlCl3, if I have to get KSP, I will assume that it is saturated. And if it is saturated, its concentration will be equals to solubility, S. And if S part of AlCl3 will ionize, right? So one AlCl3 can give you Al3 plus and 3Cl minus. So if S part of AlCl3 is dissolved, right, then S part of this can give you S part of Al3 plus and 3S part of chloride. Now you know how to get KIP. In the same way you can find KSP. Here KSP will be concentration of Al3 plus ion power 1 into concentration of chloride ion power 3. Right? And in this case, we are talking in terms of solubility. So in terms of solubility, it will be concentration of Al3 plus can be written as solubility power 1 and chloride can be written as 3S. So 3S power 3. Later on, you can do the calculation and you can find solubility. So like this, just like AlCl3, if I take any salt, if I take any electrolyte, I can find the relation between KSP and solubility. Because every time when I have to find KSP, I will assume saturated condition. And if it is saturated condition, the concentration of salt will be taken as equals to solubility, right? So sometimes you direct get question of this, expression based questions. What is the expression of KSP or KIP, or what is the expression of KSP in terms of solubility? And sometimes you get reverse question here. Like they will give you KSP and you will have to find what? Solubility, right? One more thing is there regarding your KSP and KIP collectively. Sometimes you will be getting questions of precipitations and all. So for a solution, for an electrolyte, for a salt, if the KSP value is given to you, and they are saying that we have a solution which we don't know whether it is saturated or unsaturated or super saturated, and we have to decide that whether precipitation of something will happen or not. So in that case, KSP will be given to you. You will have to find what? KIP. So KIP you can find by multiplying the concentration of ions raised to the power coefficient. And once you calculate KIP, if your KIP is greater than or equals to KSP, then you can say that precipitation will occur. Precipitation will occur. But if you calculate your KIP and your KIP is coming smaller than KSP, in that case you can say that no precipitation will happen. Why? Because when your calculated KIP is less than KSP, that means then your solution is unsaturated, right? But when your KIP is equals to KSP, it is saturated, or when KIP is greater than KSP, it is supersaturated. So in saturated or supersaturated solution only, we can expect precipitation. So sometimes they ask these types of problem regarding the precipitation and all. Right? And again, finding solubility from KSP or KSP from solubility is a very, very common question that we get in the NEET examination. So now after understanding that KIP and KSP, let's see few questions from this solubility, product and solubility. All of you read this question carefully. If you can do it by your own, please do it. Otherwise, just do it with me. Question is, the ratio of solubility of AgCl in 0.1 molar KCl solution to the solubility of AgCl in water. So here we have a question of solubility, but based on common ion effect. Based on common ion effect. Here you have to find solubility in two cases. One in pure water and one in the presence of KCl. Right? So one by one we will do. Let's say that when your AgCl is present in the pure water, right? So AgCl will decompose into Ag plus and Cl minus, right? Here, let's say that its solubility in pure water is S. So after dissociation, it will give you S part of Ag plus, S part of Cl minus. I hope you understand I am using stoichiometry here, right? One part of AgCl gives one part of Ag plus, one part of Cl minus. So S part of AgCl will give S part of Ag plus and S part of Cl minus, right? Now here, KSP will be concentration of Ag plus S power 1, concentration of Cl minus S power 1. So KSP will be equals to S square. Now, the solubility product of AgCl is given to us 10 power minus 10, right? So KSP is given to us 10 power minus 10. So 10 power minus 10 will be equals to s into s square. So from here, if you do square root, s will be 10 to the power minus 5. So please notice, this is the solubility of AgCl in the pure state without common ion effect. Now, suppose that same AgCl is present with KCl. So in your solution, when you have KCl, so KCl being a strong electrolyte, it will decompose as K plus and Cl minus, right? If KCl is 0.1 molar, so 0.1 part of KCl will decompose to give 0.1 molar K plus, 0.1 molar Cl minus. Now, if you observe here, when AgCl and KCl both are present together, the chloride ion is common. Chloride ion we are getting from AgCl also, and the chloride ion we are getting from KCl also. Now with KCl, again if I calculate its KSP, with KCl, again if I calculate its KSP, so KSP will be same, expression will be same. KSP of AgCl will be concentration of Ag plus power 1, concentration of Cl minus power 1, right? The magnitude of KSP is 10 power minus 10. The concentration of Ag plus, let's say it is S, solubility is S. But in the presence of, please focus, in the presence of KCl, because chloride is common ion, and I have told you that for common ion in any calculation you need to take total concentration. So without KCl, the concentration of chloride we were taking S. But with KCl, now the concentration of chloride ion will be S from AgCl and 0.1 from KCl. So its concentration will be S plus 0.1. And now again, right, you know very well that this solubility, because it is very much small as compared to 0.1, so this solubility will be ignored as compared to 0.1. So from here, if you get solubility, so that will be 10 power minus 10 upon 0.1, it will be 10 power minus 9. Okay, if you compare the value, you can see that without common ion effect, solubility is more. With common ion effect, solubility is less. So common ion effect, right? Once we saw that it decreases the degree of dissociation of weak electrolyte, but it also affects the solubility. Due to common ion effect, the solubility of a salt will decrease, right? And here if you find the ratio of solubility of AgCl in KCl and to that of pure water. So in KCl it is 10 power minus 9 and in pure water it is 10 power minus 5. So the ratio will come out how much? 10 power minus 4. So our answer will be what? 10 power minus 4. But I want you to focus mainly on one thing here, that without KCl the calculation is normal. KSP S square, KSP we know, S we got. But with KCl the only difference is there. While calculating KSP, we took Ag plus as S. But with KCl, the concentration of chloride ion will also be added, right, in the S. So these types of questions, I hope now you will be able to do. And of course, here the answer will be definitely A. And this is a very recent question, right? So now overall, I can say that from common ion effect, you get questions at two places. Once, calculation of alpha from K, and second, calculation of solubility from KSP. And both the time, due to common ion effect, you will notice that your calculation will become much easier, right? Now, let's do few more questions from this solubility product and ionic product. Can you do this directly? Find out, pause it, do it by your own. Find out the solubility of nickel hydroxide in 0.1 molar NaOH. Given that ionic product, it should not be ionic product, it should be solubility product. Given that solubility product of NiOH twice is 2 into 10 power minus 15. Same question is there, right? But this time you don't have to find the ratio, you have to find the solubility of nickel hydroxide, right, in the presence of NaOH. So let's do that. Let's say that NiOH twice, in the presence of NaOH, its solubility is S. So it will decompose into Ni plus 2 and twice of OH minus. So from S part, we get S part of nickel plus nickel 2 plus and 2s part of OH minus. But because we have NaOH here, so NaOH will ionize into Na plus and OH minus. 0.1 molar NaOH will give you 0.1 molar Na plus, 0.1 molar OH minus. Now, finally, if I find Ksp of nickel hydroxide, so it will be concentration of nickel 2 plus power 1, so S power 1, and concentration of OH minus is common here, right? So OH minus we are getting 2s part from nickel hydroxide and 0.1 from NaOH. So for OH minus I will have to take the total concentration. So it will be again 2s plus 0.1 and whole power 2. Now Ksp value they have given. The value of Ksp is given. How much? 2 into 10 power minus 15. So Ksp is 2 into 10 power minus 15. Now this will be equals to S into, again students, as compared to 0.1, S is very small, so this will be ignored. So 0.1 square, 0.1 can be written as 10 power minus 1. So 10 power minus 1 square is 10 power minus 2. Can you see how simple our calculation becomes because we ignored this due to common effect? Now this S will be simply 2 into 10 power minus 15 divided by 10 power minus 2, which is 2 into 10 power minus 15 plus 2 minus 13. So 2 into 10 power minus 13 will be your answer, right? Definitely answer should be D here. And yes, it is D. And this question, students, again, we got in the NEET 2020 examination. So 2 questions back to back we did of calculation of solubility from Ksp using common ion effect, and this is very important for us. That's why I have kept 2 questions from it, right? Now let's do few more questions, right? Can you do this, all of you? pH of a saturated solution of calcium hydroxide is 9. This time a connection of pH with solubility product. The solubility product Ksp of calcium hydroxide is. Now, if you know pH is 9, that means automatically here pOH will be 14 minus 9, that is 5, right? And if pOH is 5, then automatically concentration of OH minus for the solution is 10 to the power minus 5. This term is indirectly given. They have given pH. So from pH we can get pOH, from pOH we can get concentration of OH minus. Now point is, when your calcium hydroxide, it ionizes, so it produces calcium ion and twice of hydroxide ion. Now because for solution pH is given, and from pH we got the concentration of OH minus, which is 10 to the power minus 5. So that means what? We already know the concentration of OH minus, 10 power minus 5. And it is always produced in the 1:2 ratio. So if OH minus is 10 power minus 5, so calcium ion will be half of 10 power minus 5, right? It is produced in 2:1 ratio. So here it is hydroxide is 10 power minus 5. So calcium 2 plus will be automatically half of 10 power minus 5. Now, if I know the concentration of calcium and hydroxide, I can easily find the Ksp. Ksp will be what? Concentration of calcium ion, which is half into 10 power minus 5, power coefficient 1, into concentration of hydroxide ion, which is 10 power minus 5, power coefficient 2, multiply half into 10 power minus 5, and this will be 10 power minus 10. So half into 10 power minus 15. So 0.5 into 10 power minus 15 should be your answer. Which one? C option, right? C option. Now, the next question we have from the solubility product is little bit different. Now, this time you don't have to do the only calculation of solubility from Ksp, but here we have to deal in terms of precipitation. So first you read the question carefully, all of you. Question says that Ksp of, right, Ag2CrO4, AgCl, AgBr, AgI, right, are respectively 1.1 10 power minus 12, 1.8 10 power minus 10, 5 into 10 power minus 13, 8.3 into 10 power minus 17, right? Now question is, which one of the following salt will precipitate last if AgNO3 is added to the solution containing NaCl has chloride, NaBr has bromide, NaI has iodide, and Na2CrO4 has chromate. Point is, if you add AgNO3 into these NaI, Na2CrO4, NaCl, NaBr, so that AgNO3 or the Ag plus part of AgNO3 will combine to produce AgCl from NaCl, AgBr from NaBr, AgI from NaI, and Ag2CrO4 from Na2CrO4. So precipitation will happen first from the one whose solubility will be low. The one which has less solubility, right, will be easily precipitated. And here they are asking, right, which one of the following salt will precipitate last? So last precipitation will happen for that whose solubility is higher. So again, indirectly we have to do the same thing. All these salts, their KSP are known, and from the KSP, if you calculate its solubility, so the one whose solubility will be highest will have the last precipitation, and the one the solubility has lowest, so that will be the first precipitated. So if you calculate from Ag2CrO4, so roughly I am doing, right, because its solubility, its KSP will be something like S cube. So its solubility is nearly 10 power minus 4. Not exactly, but in terms of 10 power minus 4. For AgCl, the solubility will be S square. S square will be equals to KSP. So in this case, it will be nearly 10 power minus 5, the solubility value. In the third case, it will be nearly 10 power minus 6. In fourth case, it will be nearly 10 power minus 8. So clearly we can notice that Ag2CrO4 is the one. You can do the full calculation, of course. You can apply the full KSP and solubility formula. From there, you can find the solubility, right? But here, by the rough calculation, I can estimate that Ag2CrO4 here has the highest solubility. And if Ag2CrO4 has the highest solubility, so that's the one which will be precipitated at the end, at the last. So of course, in this case, answer should be D. And yes, it is D. And we got this question in AIPMT 2015. So now I think you got an idea what type of question we get from solubility, solubility product, ionic product, and regarding the precipitation part. Correct? Now, at the end, I have added a point for all of you. See, when it comes to acid-base titration, so you deal with acid-base titration in your first chapter, mole concept, right? So there you talk about how acid-base titration happens. I don't have to tell you now that when acid-base titration happens, so for any calculation, you have to apply law of equivalent, right? That equal gram equivalent of acid will react with base, right? You know very well what is equivalence point, which is theoretically calculated, what is end point, which is experimentally determined. The main thing is, when we do acid-base titration, right? So accordingly, we chose indicators. For different titration, we chose different indicators. And out of these indicators, 2 indicators are very much important to you. You need to remember it. One is phenolphthalein. One is phenolphthalein, right? Which changes color in the pH range of 8.2 to 10. So what happens when you do titration of weak acid with strong base? When you do titration of weak acid with strong base, right? So you have your titer, weak acid, you have your titrant, strong base. You will be adding strong base slowly to the solution of weak acid. Now after end point, after equivalence point, when the whole weak acid is consumed, so after that, if a small drop of strong base you add in your solution, extra, so that will make your solution highly basic. And when your solution at end point, it is basic, so there we need to use that indicator whose color change happens, right, in the basic range. Basic range means 8 to 10. So when you are having a titration of weak acid with strong base, there the preferable indicator will be phenolphthalein, right? And in case of phenolphthalein, the color changes, right? It changes from a colorless to pink solution, colorless to pink solution. And similarly, if you talk about the titration of strong acid and weak base, right? Strong acid and weak base. So in this case, in the solution of weak base, you slowly add strong acid as the titrant. So here after your end point, after your equivalence point, when the whole weak base is consumed, even a small drop of strong acid if you add, So the solution, final solution becomes highly acidic. So here you need that indicator whose color change happens in the acidic range, right? Or when the pH is in the acidic range, like 4 to 6, like methyl orange or methyl red. So out of methyl red and methyl orange, for you people, methyl orange is more important, whose pH range is 3 to 4. Means in the pH range of 3 to 4, it will change its color. So phenolphthalein and methyl orange, these two you need to remember, right? Phenolphthalein acts in basic range of pH and methyl orange acts in acidic range of pH. For phenolphthalein, color changes from colorless to pink, and for methyl orange, it is sometimes orange to yellow, the color shift we say, and sometimes we say red to yellow, right? So here I included this acid-base titration just for indicator. Please remember the range, the pH range of phenolphthalein, methyl orange, and how its color changes, and in which titration they are used. Phenolphthalein will be used when your titrant is strong base, and strong base we use for titration of weak acid. And methyl orange is used when your titrant is strong acid, and strong acid is used as a titrant when your titer is weak base. Correct? So from this also, sometimes we do get question in the examination like, can you solve it now directly from the concept that I said just now? Which indicator can be used for the titration of sodium hydroxide against oxalic acid? So you know that oxalic acid is a weak acid and sodium hydroxide is a strong base. So here what you are doing, your titer is weak acid, your titrant is a strong base. So at the end, some drops of a strong base will be added. So after end point, your solution will be basic. So here we need that indicator which functions in basic pH range, right? And 8 to 10. And in the pH range of 8 to 10, the color change normally we observe in case of phenolphthalein, right? Phenolphthalein. And for phenolphthalein, it is not pink to yellow. For phenolphthalein, it is colorless to pink, right? So in basic range, we use phenolphthalein, and for acidic range, we use methyl orange. So in this case, of course, the answer will be C. And this question, students, from the indicator part, we got in the NEET 2024 examination. Sometimes many students, what they do, they study the indicator part in the mole concept chapter itself. So anywhere you can do. Indicator you can study in mole concept, indicator you can study in the redox chapter also, or indicator you can do in ionic equilibrium chapter also, right? So now the point is, we are done with the ionic equilibrium chapter, and overall if you notice, the major part of this chapter is regarding pH calculation, right? So the technique of pH calculation, the formulas of salt, buffer, pH, right? And calculation of solubility product, ionic product, right? That's the important point. And of course, then Ostwald dilution law, which is very important because sometimes we get direct question from this. Of course, concept of acid base according to Arrhenius, Bronsted, right? And Lewis. From that also you get question. So we are done with this chapter now. Now your task is to practice as much as question as you can. In ionic equilibrium, try to solve question from each portion. Solubility product, ionic product, KSP from solubility, solubility from KSP, solubility from KSP using common ion effect, alpha from K using common ion effect, pH of strong acid, strong base, mixture of strong acid, strong base, pH of weak acid, weak base, pH of salt, pH of buffer, right? Fundamental concept of Bronsted acid base, Lewis acid base, how to identify them, how to get conjugate acid, how to get conjugate base. From each portion, try to solve as many questions as you can. And of course, for that, you know, we are providing you with the DPPs, right? So get that from the video description or from the PW app. So thank you so much. We'll meet in the next one-shot video. Bye-bye. Over on